Okay. You are using computer audio? Yeah. Yes, sir. So live stream is working.
Hi, who is this FSTTCS 2020?
Hey,
Hello. Hi, who is this FSTTCS 2020? Hey. Hello. Hi, who is this FSTTCS 2020?
Hi, uh, uh, Shantanu.
Hello? Yes, sir. You can hear me?
Can you make
Yes,
a
sir.
co-host?
Whom should I make host?
FSTTCS 2020.
It is already co-host.
Okay. By default,
FSTT.
can you make
Yes, sir.
Aishwarya as a co-host, and I mean you can just make
Yeah.
it Aishwarya as a co-host. Hi Aishwarya, Bhaskar here. Just we promoted you as a co-host, and
Oh, thank you. Hi, Bhaskar.
yeah. So Shantanu, I will log out and log in as a Bhaskar, and okay. So
Okay.
yeah.
Okay,
Yeah,
yes,
that's
sir.
better.
Shantanu will manage, right? So you have to make
Yes,
a jam. You have to make.
Hello?
So Shantanu, can you hear me?
Hello, I can't hear you.
1 second. Can you hear me now?
Yes, sir. Yes, sir.
As soon as Professor Jam joined, you have to make him as a
Host.
host.
Yes, sir.
Okay, so then you be there. Only if there's a problem with this connection, you become host again.
Yeah.
As soon as he joined back, you have to make him host again. I mean, so you have to give the pass that thing. So I'm
Yes,
going
sir.
to
Yes, sir.
Shantanu?
Yes, sir.
Can you make me a host?
Yeah, I'll make you host. I'll make you host or co-host? Host, right?
Host, just host. Just
Yes.
do.
Yeah.
So, and there is a way to climb host. Can you climb back?
Claim back.
We
Okay.
claim host. There's a option. There's the bottom of the participants. You click the participants.
Yeah, I got it. Yeah.
Claim host will be there.
I reclaimed host. Yes.
Yeah, you are the host now. So now can you pass the this thing? The YouTube link?
Yeah. I'll pause the YouTube link. Is it?
The stream, YouTube stream, and then start again.
Okay.
Wait for a second. And
Okay.
you stop. Did you stop it?
I stopped it and then started again. Sorry.
Okay, fine.
Wait.
So you know that nothing will happen to the live stream will run on. Okay.
Okay.
Now you know everything to be done. What is to be done?
Yes.
Okay, so
yes.
All clear.
Yes, sir.
All clear.
Yes, sir. Yes, sir.
Hello, hello, hello.
Hi. Dietmar?
Anybody hear me?
Can you enable me so I can share screen?
Yeah, hello. We are waiting for Professor Jam Ramanujam, and
Yeah.
I hope he will join in a couple of minutes. And in the meantime, is there anything
But
else?
are you the host? Because I need to share screen.
Screen. Okay, I'm going to give you a hope.
I'm Rosemary Nagel, and
I'm speaking. Is anybody hear me?
Yes.
We can all hear you. Yes.
Can anybody hear me?
Yeah, if you are Michel, I can hear you.
Okay, thank you. I cannot use my webcam. I don't know why. Start video does not work. Okay.
But can you let me share screen?
Just a moment, ma'am. 1 second. Few minutes. Hello, ma'am.
Yes.
You become a co-host now. You can share your screen. Can you just check?
Okay, good. Let me see which one.
Hello, Rosemary.
Let's see. I should get out of a quick PowerPoint so I don't.
Hi, Dietmar.
Hey, Bhaskar. Nice to see you.
Good to see you. It seems Jam is not joining it, so we'll make you as a host. Is it okay? You will manage?
Yes, perfect. Yes.
Shantanu, you can make Dietmar Berwanger as a host. And
Okay, thank you. I will just give me a minute.
Sir, done. Yes, sir, done.
Yeah, good.
And I will be there.
Okay, and I will try. Hello. I will try to upload my slides afterwards. I'm not sure you hear me.
Yes, I can hear you.
Okay, I'm sorry,
Yes.
but my webcam does not work. I'm trying to start the video, so you cannot see me.
Jam.
So I see Indians here.
Wow, Jam, you got a new haircut. So actually, Bhaskar, I have one slide to keep in the background during the opening, and then there will be Rosemary's slide. Is it possible to have two files in the background?
No, I don't know about now. It's what you can do is you can share your screen with that slide
Okay,
and then change.
perfect.
Yeah, that would be a better. You are the host.
Can I just try to share my screen, please?
So I'm sharing my screen.
Michelle,
Yes?
hello, good morning.
Sir, you have mic is muted. I think we can't
I
hear you.
cannot hear anything now.
Yeah.
Of whom? Of Michelle? Let me check.
Jam is. Yeah, now he is.
Yes. Hello, Mina.
Hello.
Hey.
Hi.
Nice to see you.
Mhm.
Okay. Didn't have time to.
Too smart enough?
Front, left.
Shall I put the Zoom link on the Slack channel for this workshop also?
That would be great. Yeah.
Oh, yes, indeed.
Because the Slack channel is also visible only to registered
I
participants.
cannot hear you. Boy. Dietmar, can you speak? I cannot hear.
I can hear you very well.
Okay, I cannot hear you.
Okay, Mina can hear me, Rosemary can hear me. Let's go to the chat.
Can Michelle hear anybody else? Or is it that he just can't hear you?
Let me check your settings. Okay.
I cannot hear.
He says he cannot hear anything.
And I cannot share my video.
I think just send a chat
We
message.
can make you co-host for the no, maybe. So
yeah, we can make him co-host and then check.
yes. So
but his ability to not to hear means that it has nothing to do with that. I think
yes.
if he can't hear anything, he has to retry. Probably some audio problem in his computer.
Wait, I can try to call him.
Front, left.
Sent a message.
Okay.
Hey, Ashwarya. Okay, let's see.
Hi, Dietmar.
Hey. Hey, nice to see you.
How are you?
Very well. Very excited.
It seems I can speak, but I can't hear you.
You cannot hear us. Check. Okay. Entering after killing and restarting browser. You did this, and you can. We can hear you.
Front, left.
Okay, I speak, but you can't hear me. Yes, you can. I cannot. Okay. D'où ça vient ce truc? Paramètres.
Jam, in the meantime, it's already we are live streaming it. If you want, you can tell us. We'll stop and start.
Okay, I'm going to do that.
Let it be. I mean, it's fine. We're going to start in a few minutes, couple of minutes anyway.
Hello, Anup. Actually, we should allow a couple of minutes for people to arrive because I can imagine many people just click at 2 p.m.
Many people start searching for the link to click at 2 p.m. So I will try to share my screen. Actually, it also offers me to share files. So Rosemary, can we try? I share my screen for a moment, and then you put back yours. Can you see my screen?
Yes, it's visible.
Perfect. And now Rosemary, I stop sharing and see whether Rosemary's slides come back. Ah, wonderful.
You see my screen?
Perfect. So we go back to the first slide just for the introduction. Bhaskar?
Yeah.
Is there anything technical that we should tell people, except that the session is streamed and they can ask questions?
Yeah.
I mean, everybody who is following.
Post the questions on the chat box.
Yes.
And unless they need to interrupt immediately and desperately. Yeah. I think that's simple.
Okay, you see me, but I cannot hear you. So that's the mystery.
Already, it's very good. We can see you. You cannot hear us. Okay. It's wonderful. Let's see. So. Hello, Sasha. Hello, Laurent. Wonderful. So, from somewhere there are this called accessibility instructions coming, like cursor left, cursor right. Maybe it's the camera switching. Okay.
Dietmar, can you hear me? I cannot hear you.
I can hear you.
I cannot hear anybody. Okay, I don't get it.
Okay. Yes.
Dietmar, I think we can start off now. I think people will come in.
So with the timing, unfortunately, I cannot see the timer on my screen.
Just let me know, Rosemary, when you're ready.
Yeah, I'm ready. It's just with the timing. I have to think a little bit what I do with the timing. I don't have a big clock. Yeah.
Okay. So we will start now. Welcome everybody to our FSTTCS workshop on strategies for uncertainty. This is a workshop on the intersection between game theory and computer science. We are all concerned about information, but what is different is the way to look what is beyond information. In computing, there is much about composing. So we try to incorporate what is uncertain in basic atoms, and then we build on them. And in game theory, the idea is to start looking at the world composed as it is, and then thinking about what the parts should do in relation to the others. And the purpose of the workshop is to see through flashlights different ways to capture uncertainty, to understand where it comes from, to find ways of representing it, to see how it propagates during composition and decomposition. So we have a series of 5 keynotes and 5 lightning talks. Our first speaker today is Rosemarie Nagel. She has been working for a long time now on behavioral game theory, which is looking to identify the game theory games that are behind the way interaction develops in reality. And one of the central concerns of Rosemarie was to structure the space of games that are actually played in terms of a theoretic body. So she will talk about zero intelligence, how to harness zero intelligence, and idiosyncratic signals in beauty contest games. Rosemarie, the floor is yours.
Okay. Let's see. I have to share screen. And can you see my screen?
Not yet.
Okay. Let's see.
It takes a minute.
Okay, very good. Here is my screen.
Perfect.
So can you now
can
see my screen?
Yes.
Okay, I just have to adjust. Okay, thank you very much for this invitation. I'm very excited to talk to you. It's the first time actually that I talk to in a workshop directed to computer scientists. So my title is How to Harness Zero Intelligence, Idiosyncratic Signals in Beauty Contest Games. And since this is a workshop on strategies for uncertainty, I'm the first speaker. I first want to talk about the question, what is strategic uncertainty? And if you think of strategic uncertainty, you have to also think about structural uncertainty and risk or ambiguity. So let me give you some definitions. So strategic uncertainty, how we as experimenters see it, is about uncertainty about the actions and beliefs, including beliefs of others. And we always involve human opponents. So it's always in a strategic interaction. There's also structural uncertainty, and that is also called parametric uncertainty, which concerns the characteristics of the situation. So there could be, for example, unknown parameters of the model, which you as informatic scientists also know. There is something very different in individual decision-making that's called risk. And this was coined by Knight and Keynes. And they talk about risk when they think about known probabilities about situations and very structural represented. These are typically lotteries. So you have states of the world and you have probabilities of these states and you have outcomes for each state. But then on the other hand, there is ambiguity, which means that there are unknown probabilities about situations. And so you have to form subjective probabilities. And that was coined by Savage. And Ellsberg did one of the first experiments about ambiguity and risk. And he finds that subjects have preference for risk over ambiguity. That means they like lotteries more with given probabilities than if they are not given. So I will talk about these features in different ways in my talk. And now I want to show you what I mean by uncertainty, risk, or ambiguity in beauty contest games. So I first define the uncertainty. So we don't have structural uncertainties. All the parameters of the game are known. So that means the subjects really know what are the actions phase, what are the interactions, what the rules of interactions, and what is the payoff outcomes and how many players are there. However, they have strategic uncertainty. That's the main problem. So the subjects don't know each other. There's no friendship, for example. If there was friendship, maybe then they could know how the other person reacts. And all these games I'm presenting to you are fresh situations. So no subject has experience or should have experience. So we choose only subjects that have no experience, and there's no reputation. And typically subjects don't know the strategic sophistication of others. So the sophistication could be between no intelligence and full rationality, and there's no common knowledge about it. Of course, I invited you to play one of the games, and I asked you to play against other people from the conference, and maybe there you think, well, they do some calculations, maybe we can know what they are doing. But in general, the subjects don't know each other. And the simplest characterization then of the opponent's behavior could be zero intelligence. And maybe also the simplest characteristic of opponent's behavior could be rationality and common knowledge of rationality. And that's what basically is used in economics. This is also a simplest characterization of opponents. So we can also have uncertainty about what other information is. And we include that also in one single experiment. And the title actually comes from that. So we can allow private signals. And if everybody gets a signal, typically when we want to calculate a game theoretic solution, we need to know a probability distribution from where the signals are drawn. So that is something like bringing in risk. So there are known probabilities. But there is, of course, ambiguity because, I cannot easily formulate probabilities of the behavior of the others. Of course, I could formulate subjective probabilities. I could think if there are strategies A and B, I could think the others choose randomly or uniform randomly. So I could produce subjective probabilities about other players' behavior. And in part, we are exactly doing that, introducing subjective probabilities. So what do I mean by zero intelligence in beauty contest games or in general? So typically, zero intelligence means that such players ignore the information of the situations and the existence of others altogether. But we have to model it, and typically we model it as random behavior given a probability distribution. And this probability distribution of course, has to be within the possibilities of the situation. So, for example, one cannot choose outside the action space. Yeah, so if you program it, you would say, the action space is, like in our case, often 0 to 100. So that's the probability distribution would be over this action space. And I add here in parentheses, there could be a refinement for zero intelligence behavior over time. For example, if the action space shrinks, a zero intelligence agent also would only choose within this shrinking action space. But this, I mean, this has to be formulated for each situation in a more parsimonious way, given the situations. We will not concern about the last point in general here. So let me state what Herbert Simon, John von Neumann, and John Case said about zero intelligence and how to put some intelligence into such a model. So Herb Simon talked to Sharm Sander, who actually formulated together with Gold the first zero intelligence model in 1992 in economics, actually in a double auction experiment. And Simon seeing Sharm Sander's experiment and model said, put a bit of more intelligence into ZI. And probably some of you know or should know Herb Simon. Herb Simon was a social scientist. He really worked in economics, psychology, social psychology, cognitive psychology, and also in computer science. And in computer science, he's probably best known his work on artificial intelligence. And he also got a Nobel Prize in 1978 in economics. So that's Herb's. That's Simon. And Simon says in 96 in his last book about zero intelligence in a quantity choosing model, oligopoly model. Each firm with limited cleverness formed an expectation of its competitor's reaction to its actions, but that each carried the analysis only one move deep. So that's Kono. You give basically best reply to what you have seen in the past. But what if one of the firms, or both, tries to take into account the reaction to the direction? They may be led into an infinite regress of outguessing. So basically, Simon connects zero intelligence to full rationality, but he doesn't know really where to stop. And that was a main problem in economics still at the time of 1996, where the formulation, at least in theory, was not so clear what would it mean to have bounded rationality or stop this procedure. Von Neumann comes from the other end, and he says, this is the principle of classical economics. How is the absolutely selfish Homo economicus going to act under given external circumstances? Maybe how is he going to act against zero intelligence? So basically, Simon comes from zero intelligence, and how do you get to full rationality? And von Neumann says, well, if we have full rationality, we know basically what to do. Well, still in 1932, game theory was not fully, or was not at all formulated for general games. But he basically sees that there's a problem if we start with full rationality. And Keynes basically formulates a metaphor, which comes the closest to my talk. So he basically says there are beauty contest games, and in which the prize to the competitor is given to the competitor who predicts the average preference of all competitors. And he also formulates a behavioral model in the following a little bit abbreviated way. So a competitor has to pick not those faces which he himself finds prettiest, so that would be zero intelligence. You just think, who do you find the most prettiest? No, we have to devote our intelligences to anticipating what average opinion expects the average opinion to be. And there are some, I believe, who practice the fourth, fifth, and higher degree. So that's basically what I want to say as an introduction. And additionally, I give you now the 3 questions related to strategic uncertainty and ZI, which I will formulate and try to answer in this talk. So the first question is how to bridge difference between ZI, a bit more intelligence, to ZI, and full rationality. And one of the first models that structure bounded rationality was a step-level reasoning model, which I introduced together with beauty contest experiments, and that's nowadays called level K or cognitive hierarchy. The second question I want to answer is, how does structure of situation influence average behavior or maybe zero intelligence? And for that, I introduce variations of the beauty contest games. And other people have done that with other games. Yeah, so there's a 30 years of literature, and I just confine myself to beauty contest games. And the third question then is, if behavior is very far away, maybe from an efficient equilibrium, how can we create institutions, that's a general question in economics, that mitigates the bad choices of zero intelligence? Yeah, because if people react to zero intelligence and maybe they cannot play the optimal choice because there are too many people who are far away from this optimal choice, then we should see how to mitigate that with good institutions. And the last variation I will introduce is that actually the average or naive behavior is an equilibrium choice. So that's a very simple trick. So if I basically give an anchor, which is the equilibrium choice, then everybody can choose the equilibrium. Okay, so that's the introduction. And if you have a question, please ask your question immediately. So I like actually talks with lively discussion inside the talk already. So if you have questions about like understanding question, please definitely ask them, and also other interesting or other questions I would like to hear already during the talk. So are there any questions so far? Well, no questions yet. So our first question, we want to bridge the gap between ZI and common full rationality. And we do that with the original beauty contest game, which I did in my thesis actually. And I spice it also with brain data, and I will introduce you to the level K model. So the original guessing game experiment was the following, very simple. It's actually one of the simplest games in terms of the instructions. So all participants choose a number between 0 and 100, and the winner is the person closest to the whose choice is closest to 2/3 of all chosen numbers. And more formally, that just means yi is equal to 2/3 of the average, and yi is the own choice. And the winner will receive just 10 euros, and this is split if there are ties. We also ask subjects for comments. So we give them an empty sheet of paper and we say, please give us your comment. And the subjects know how many participants there are. They actually, this was done in 1990, and this was done with, the experiment was done without a computer. So it was in a large classroom where players sat far away from each other so that they couldn't see what the others are doing. And we also repeated this game with the same subjects, but today I will only talk about first period behavior, so where subjects have no experience with the others and also no experience with the game. So it's really strategic uncertainty. So we can already formulate the game theoretic solution to this problem. So since the interval is from 0 to 100, 100 is the highest possible average, and the best response would be 66.66, and all numbers above that are weakly dominated strategies. So you win with 66, but you win also with higher numbers. That's why the other numbers only weakly dominated. However, if everybody would think that, then you would come to a best reply to 44, and so on until equilibrium is reached after infinite steps of reasoning in an interval from 0 to 100, and the numbers are from the real set. Yeah. So that's the equilibrium, 0. So the question is, do people choose the equilibrium? Well, people don't choose the equilibrium, but they choose typically higher than the equilibrium. But is there structure? Can we say something more about strategic uncertainty than saying they are not playing the equilibrium? And that was basically the big introduction of level K, and the introduction of structuring some behavior, which seems to some people like random behavior. So I give you here my lab data, which you see here on the upper left, and all the other experiments that were done until 2002, with classroom data, with take-home data, with economists in conferences. So I would do in a conference before starting the experiment by hand. So I would distribute pieces of paper. And then we did also experiments with 3 newspapers, Financial Times, that was done by Richard Taylor, and Spektrum der Wissenschaft and Expansion. And then one subject actually did an experiment because he couldn't figure out what one should do. And he did an experiment with a news group, and you see these 2 means are amazingly close. So there is more than just random behavior. So opening the black box of what happens in the brain or how people react can be structured. And you see there are this is the x-axis is the numbers between 0 and 100, and the y-axis are the relative frequencies of each number. And we can actually structure the game by saying there's choices around A, B, C, and infinity, and that A means just 33, B means 22, C means 14 or 15, and infinity. Yeah, so game theoretical solution would say 0. We see spikes at 67, but we don't really see interesting spikes at 44 or 29. So I did a statistical test about that. And we did also a mixture model test for all this data, yeah, to show that there is really clear pattern, albeit that the frequencies, the relative frequencies can be different. So for example, in lab data, there are no zeros. And when economists play amongst themselves, there are a lot of zeros. So there are more than 20% zeros. Yeah, but the spikes are at the same points. That's what our mixture model shows very nicely. So let me come now to the behavioral model that was formulated for this kind of games. So we have to ask ourselves, so how do you start the thinking process? So game theory says you start at 100, but the spikes are not at 67. The spikes start with 33. So 33 is just 50 times 2/3. Therefore, level 0 is just your favorite number, a Salient number, focal number, or just a uniform random. And the mixture model shows that there is a uniform random distribution. And then best reply to that wouldn't just mean a little bit more intelligence and you land at 33. When you have theory of mind, so you think that the others are also thinking entities, then you come to 22. More generally, you have 50 times 2/3 to the power of k. And eventually you reach equilibrium, which is the rational expectation equilibrium. And you can also reach it through a fixed point, because 0 times 2/3 is 0. Therefore, you should choose 0 if you think that this is what other players do. Of course, you have to add noise to explain also the data near 33 or 22. And so that's why we have a mixture model eventually. And there are variations. So higher level players here give just think that the others are all one step lower than yourself. But you can, of course, also give best response to a distribution of lower levels. And there's also a cognitive hierarchy model by Karma Hong and Chong, and they introduce a Poisson distribution. So basically, you you have a you believe that all the others are just if you're a level K player, then you think all others are below from level 0 to level K minus 1. Okay, so let me give you a very quick hint to brain data. So Giorgio Coricelli and I did an experiment by putting people into an fMRI machine. And obviously, if you do fMRI and neuroscientific talks, tools, then you cannot just ask people for one number, you have to ask for several numbers. And what we did, basically, we asked not only for 2/3 times the average, but 1/2 times the average, and 1/3, etc., or 4/3. And so we got a lot of choices and could classify the behavior of the subjects according to choosing level 1 or choosing level 2 and higher. So we didn't find random behavior because also we let them play against the machine, which just chooses a random number. And then the best is 50 times 1/2 or 50 times 2/3. So we didn't get random behavior. But we very clearly see a difference then in certain areas, and I am just showing you 2 areas which are particularly interesting in terms of theory of mind areas, which is the medial prefrontal cortex. So if you zoom in to and you take all the high level of reasoners, then you see clear, distinct activity in the medial prefrontal cortex for those players, but you don't see that differentially. Always in comparison to a baseline. The low level of reasoners, they show more activity in the right anterior cingulate cortex, which is actually a area for self-reflection. So other neuroscientists, of course, did a lot of experiments on these kinds of areas. So and there is a clear theory of mind, so thinking what the others are thinking in the medial prefrontal cortex. So that was only a quick introduction to brain data. So that was about question 1. So the question 1 was, is there a pattern of behavior in the original game? And we introduced the level K model. Now, how does different structure influence behavior? So not only zero intelligence behavior, but how do more sophisticated players react to the structure and to maybe reactions of zero intelligent agents. And then the third question is, what design brings behavior to near equilibrium? And we show 4 variations of beauty contest games, and one of the variation I also introduced to you in an online experiment. So in all 4 variations, there are no repetitions. There are different subjects for each variation, and mostly they are undergraduates, but also I will show you the behavior of your of the conference participants who participate in this experiment. So in order to introduce the 4 variations, I give you a more general equation of the beauty contest game, so a generalized beauty contest game, and then I show you what kind of variations we do. So the generalized beauty contest game is actually a class of, contains a class of games which are aggregative games. So, and I will show you immediately what that is. So basically your choice, YI, is the best response for player I to the behavior of the others. So that would be in our case here, the average of the other players in the same time period. So we can also have a time period. We will always have t equal to 0 now. Yes, so we will not think about how players react to what they think is the behavior of tomorrow. So this is important in economics when you think of inflation. Yeah, what the price of today could be influenced by the inflation predictions of tomorrow. So this is the main feature here, P times the average. And we can vary the P. So that will be our one of our variations. the parameter here we vary. And then we can also add a constant, and this will be 10. And that's your online experiment. And we can add also some idiosyncratic signals. So that's from the title. And we put here an expectation in front of it. And so the expectation about all this is here. So we have an expectation, we have an aggregation function, which can be the average, the median, the sum, the max or min, or C is a constant, it's a fundamental value. This constant might be known or not known. In our case, it's always known. And the parameters can actually be negative. Then we have a game of strategic substitutes, and I will explain that more for each variation. And here we put this to 0. Or it can be positive, which was in our first example. That means strategic complements, and I will explain that also later on. And then we can introduce exogenous, idiosyncratic, noisy variables. Yeah, and we need, when we introduce that, we need to know, and the subjects need to know from where these signals are drawn from. Okay, so that's the general introduction. And so we will vary P, positive and negative, vary C, which is 0 or 10. And
sorry, Rosemary, we have one question from Jen.
Yeah.
Yeah. Rosemary, does it matter whether n is small, large, or you just treat this whole thing as a function of n? Would behavior matter, like when you're playing against 10 players or 20 players, as opposed to, let's say, 100 players?
Okay, so game theoretically, there's no difference whether it's 10, 100,000. But game theory, it matters very much if it's only 2 players. Yeah, because with 2 players, 0 is actually a dominant strategy. Yeah, and we have a paper on that. I will not talk about that. If we have 10 or 100, it doesn't matter really much. So if you think of the formula, when there are 10, the influence of each player is not so big. But of course, the variance can be bigger. Yeah, so it matters more when you have 3 or 4, because then the single person matters much more. So the behavior is less predictable. So the 50 times 2/3 is much better for a large audience. So let's say 15 or larger than for a smaller audience. Yeah. Is that an answer to your question?
Yeah,
so I showed it a bit here in this. You see 50 times 2/3. I mean, people choose 33 or near, but here they choose more 25. Yeah. Which the more players you have in this, we have maybe 100 players. The more players you have, the more precise is the model of 50 times 2/3. So people then really react precisely to this model, to this 50 times 2/3. Yeah. While when it's smaller, then you might choose more like to the next prominent number. Yeah, but otherwise you see here 50. I should have said that here in every session there are 50 independent sessions. So in one invitation there are 15, and here there are 2,000. Yeah, but you see, it matters more who the players are than how many there are.
I also have actually 2 questions.
Yeah. Oh, I don't hear you.
So value, suggesting the correct value. And actually, I mean, it's completely different from what theory would say. I mean, theory would tell you choose a 0, no? And it is correct in the sense that everybody chooses it. So you should rather stick to, I mean, yeah, I was puzzled by this transition in the notion of preciseness, correctness. It's a value that doesn't make much sense theoretically. But
no, theoretically it makes sense, but behaviorally it doesn't make sense.
I mean, the 33.
The 33
It makes sense
no
only behavior.
Ah.
No, I mean, the only reason to believe in the 33 is because it will be chosen. I mean, that's the only reason. There is no, I mean, the theory, classical theory would tell you 0 should be chosen. This is what we should recommend. This is what we should learn. But my question was also about these exogenous values. So it is it goes into the aggregation, and it's associated to the player who calculates an expectation. Is this right? So why should I disturb my expectation? If you go to the formula, pardon me.
In which sense disturb? In which sense?
Can we go to see the general formula for the beauty contest with the epsilon I?
Oh, we are not yet with the epsilon I.
No, this was on the so the general formula that you showed.
Yeah. Oops, here.
When you introduced, yes. So this epsilon I, in the end, so we say my choice is the best response to something that I get by aggregating what the others do. Then I add this substitute or complement, and then I have this exogenous factor that is private to a player. So because this was not in the setup that you gave us.
Let me come to that
okay.
in a few minutes. It's better to come to that in a few minutes.
Yes.
So let me introduce the first. So I have to hurry a little bit. So I don't know how many minutes I have left. It's now 10:09. We like half an hour. Or 20 minutes. Well, okay. So now we introduce the first variation, which is an unbounded interval. So before we had from 0 to 100, and now we do only one little difference, that you choose basically from -infinity to +infinity, or in other words, you choose from R, the entire line, but it's still 2/3 of the average. So the payoff function we change now, and we say 100 minus choice minus the 2/3 of the average. So everybody gets paid, and you have to be as close as possible. You have to minimize the distance. And there's a slight difference in theory, which makes no difference in practice. So all should choose 0 in both of them. So if you have from 0 to 100, we have the iterated elimination of strictly dominated strategies. And in the unbounded, we can only use the fixed point argument. So what would be the level K behavior for the unbounded set? Well, if ZIs choose between negative and positive numbers, maybe the average is 0, so we should immediately all choose 0. But this is not the case. Quite contrary. So here we show now cumulative distribution. So here are, again, the numbers from 0 to 100. There's nobody choosing a negative number. That's the first observation. This cumulative red line is what I showed you before. Yeah, it's a bounded interval with a lot of people choosing around 33, 22, some about 50, but otherwise quite random. But the average is around 33. So the unbounded is very much different. So the average is now 14. Yeah, and how can we say that? Well, we first introduced this level K model. If we have the unbounded, basically people realize that 0 is the correct number. So they choose very close to 0, as in the newspaper experiments. We know that people who come to 0, they don't choose it, but they stay around 50. Yeah, and we see that also lower than 10. And we see that also here, that more than 50% basically choose around 10 and lower. Yeah, but so for this is one of the few variations where we don't have really a level K story, because level K would be 0. So that is the first variation. So we get behavior very much closer to the equilibrium, namely to 14, while before it was 36. Yeah, and game theoretically, there is absolutely no difference between the two. Okay, that was variation 2. So we have 4 variations. Now I give you variation 2. That is also very simple. So we introduce -2/3 of the average. Yeah, otherwise everything is the same, and we only look at unbounded choice sets from variation 1. Yeah, so again, equilibrium, of course, should be 0, all should play 0. And we have no level K model for the positive parameters as shown in variation 1. And the level K for negative parameters actually exist. And what is that? It's very simple. So this is the unbounded, is the blue. That's the strategic complements. So let me introduce quickly complements and substitutes. So when I know other people choose high numbers, I should also choose high numbers. So if people think the average is 50, then I should choose a high number, 33. But in the negative one, if everybody chooses a negative number, and you see a lot of people, namely more than 40%, choose a negative number. Yeah, so if everybody chooses a negative number, which is minus 2/3 of the average in signals, I should choose a positive number. And we see that there are about 25% who choose a positive number. And we have here, finally, more than 20% who choose really 0 or very close to 0. Yeah, so finally we get this. And indeed, when we have environments with strategic substitutes, you're closer to the equilibrium. This is, so basically when you have complements, that is an environment of where bubbles are created. So if we think of the housing market, that is a market of complements, while normal goods are more in an environment of substitutes. So again, the equilibrium is reached in the negative range. So it's the mean is 1.9. That comes just from the fact that there are positive and negative numbers on both sides. And in the blue domain, basically, the mean is 14, as we saw before. And level K basically oscillates. So if everybody chooses a positive number, a negative number, I should choose a positive number. And if everybody chooses a positive number, I should choose a negative number. Whether you are a high level of reasoner or not, we cannot see. But with fMRI, we probably could see whether you are high or low reasoning, because in the medial prefrontal cortex, we could see the more activity you have, the higher is the chance that this correlates with higher level of reasoning. Okay, that was variation 2. Now I come to variation 3, which is actually the variation I played with you. And here I just introduce C. And we allow the interval to be unbounded or bounded. So we have 2 treatments, yeah, unbounded and bounded. So that's the general formula. The equilibrium now is 30. This is just a fixed point. So if you plug in 30 here, then you will see 30 is equal to 2/3 times the average plus 10. So again, if you have a bounded interval, we have rationalizability of iterated elimination of dominant strategies from above and below. If it's unbounded, you don't have that. And I will now explain to you the level K for the bounded and unbounded set in more detail. Yeah. So I hope you all understand the setup. So it's 2/3 times the average plus 10, bounded or unbounded. And the bounded set we show with the blue figure, and the unbounded with the red. And you see that in the bounded set, actually players, we will show that in the data, start with 50, because again, I have to choose between 0 and 100. And so the average would be 50. 2/3 of that is 33 plus 10 is 43. So that would be level 1. Level 2 would be 38, and level 3, 35, until you reach 0. On the other hand, if you are in the unbounded set, level 0 can be 10 or 0. Yeah, so you have 10. 2/3 of that is 6.6. And plus 10 is 16.7. So we count that as level 1. and so on until you get 30. So the question is, do we see the averages very low in the unbounded set or very high in the bounded set? And again, are there negative numbers? No, there are no negative numbers. Yeah. So here we have the distribution. Yeah. So that's the bounded set. This is the unbounded set. And there is an amazing difference. I mean, you don't need to do any tests. The equilibrium is 30. And now I show you graphically the level of reasoning. So when we are in the bounded set, we start at 50, and level 1 is at 43. And you see 20% are zoomed directly on there, and we can count a little bit more. And we have also a few who choose near 0. And here, I mean, we see people also who come from the other side, but this is only 25%. So 75% are above the equilibrium, while for the unbounded, 85%, almost 90% are below the equilibrium, and that is shown with level 1 reasoning. Yeah, so we get in fact the mean is 14.53 in the unbounded set. So this is really level 1, while it is 42, so close to 43 in the bounded set. So I played the game with you, and let me show you just the averages of those people who played against the undergrads. So I asked not only that you play against yourself, your group, but I also asked to play against the undergrads. So let me first just show you the mean of the undergrads. So like in the undergrads, in the bounded set, your number is much lower than in the unbounded set. In the unbounded, it's much lower than in the bounded. So indeed, you capture that. And here we see that basically in the bounded set, you play on average very similar. Even the variance is very similar. But your target is now 38. Yeah, so you have to be closest to 38. And indeed, 43. So level 2 is more or less 38, 39. So on you are basically on target. You catch the mean player catches that. While in the bounded set, actually you play level 2 on average. Yeah, and indeed level 2 would be 19.6. So you're closer to the mean of your choice is closer to the undergrad target than the undergrads themselves. Yeah. So you understand it's very important to think of the sophistication of the others. So here I show you your data set. I mean, we have only few observations. So basically we have 11 to 15 in all of them. So let us first look in the unbounded set. So this is the blue and the red line. Yeah. Basically for the blue, you have 3 types. You have those who choose 0. Yeah, these are about 20%. Then those who choose 16, so that's level 1, and those who choose equilibrium. Yeah, so the blue line goes only to the equilibrium. Yeah, so that's why you are quite good because of these equilibrium players. And I mean, basically nobody is level 2. Yeah, but on average you're level 2. So you see how bad it is to just look at the mean. Yeah, so nobody would get the really big prize. And this is similar of those who play against. When you play against yourself, there are more that approximately the same number of people who choose the equilibrium. That's from here. And again, you also think, I mean, less play 0, and but a similar amount of players play level 1. So we have the same 3 basically mixtures. When you play the unbounded, you play, whether you play against workshop or undergrads, that's pretty similar. Yeah, as we have seen before. So on average, you're more or less 43. So here I repeat the one from before. Against undergrads, you are level 2 players, and level 1 player on average against your own in the bounded set. Yeah, when you play against the workshop, basically you play on average equilibrium, most players. I mean, the mean is the equilibrium, and the target then is also the equilibrium. So these players really win. Yeah, so it's correct to play the equilibrium when you play against yourself. Yeah, in the unbounded, you are pretty much the same. Yeah. So now let's come to the, yeah, I will leave this out for time restrictions. Let's just come to variation, sorry, that should be variation 4. We add an idiosyncratic signal. So as I said to you, I want to find, first of all, I want to find how zero intelligence and the average behavior varies with different structures of behavior. So when we change a parametric, the parameters of the game, and which are all known. And now it was more or less through chance that I met Jesper Habib, who is a macroeconomist. And he actually presented a model, which is a beauty contest model, which is a simplification of the general equilibrium model. And what is the general equilibrium model? But basically, it's where firms and consumers interact, and all are price takers. Yeah, so the prices of the goods and the wages, they are all determined basically through, one could think of a double auction. Everything is done simultaneously in a double auction. And Jess introduced into this big general equilibrium model idiosyncratic signals by the consumers. So the consumers have some ideas, so the animal spirit about prices and wages, and they send these signals to the firms, and who could actually take the signals and formulate prices and wages. And the simplification of that is what you see here. It's basically a beauty contest game where you just add these idiosyncratic signals, which are exogenously introduced by the consumers to all the firms. So the basically decision makers are firms who, for example, set prices. Yeah, and these idiosyncratic signals, in order to calculate the equilibrium, you need to know the distribution, and the distribution here is 0 and 10. Yeah, and in this case, everybody has to choose their signals, or they can also choose 0. Yeah, but in general, the equilibrium is all choose their signals. So if you get a signal like 5, choose a number between, choose any number, because we have normal distributions, we need the unbounded set. Yeah, and so you get a signal and you have to choose 2/3 times the average plus 5. And others get -5, so that on average, the signals are 0. Well, if the signals are 0 on average, then obviously 2/3 of the average will be 0, and then you add your 5, and then this is exactly what you have to play. Yeah, this equilibrium is indeed more complicated to derive, but zero intelligence agents, or agents who just work by intuition, very easily choose 5 or a similar number, a number near there. And so level 1 reasoning is also choose your signal. And well, will we see that? Well, the title suggests that we can harness zero intelligence by this treatment. And here it is. So we have yi is equal to plus or minus 2/3 times the average. So we can just, it doesn't matter whether it's positive or negative, plus this epsilon I. And you see the distributions are very close to 0. Yeah, and indeed, since people get signals between basically -10 and +10, that's where they should choose from. And here, finally, the averages are very close to 0, and the standard deviations are very low. And the target then is closer also to 0 plus your epsilon I. Yeah, and a last slide of data I want to show you is basically what are their choices. So these are the choices with the 0 in the midpoint. The red line is basically the normal distribution, so as you would get it from a standard textbook. Of course, when you draw signals, this is in gray, yeah, then you get not a nice normal distribution with so few data, but it's pretty close to that. And the black line is the data for the minus 2/3 of the average, and you see that many people choose 0. So they don't choose, well, I mean, here we don't show whether there's a correspondence between the signal and your choice. Here we only show the relative frequencies of choices, and the drawn signals are separate from that. Yeah. So what we see that this mimics in some way the normal distribution. If we also show basically whether people choose their signals, we see that indeed 30% choose their signals, and there are still some 10% who choose near 0. Yeah, so they ignore their signals. Yeah, so this is the last treatment I wanted to introduce, and so we finally have harnessed zero intelligence. And so as a discussion, I just have these few points. We talk about strategic uncertainty. We have a parsimonious model to open the black box, to structure what's in the black box. And this has been applied in many different areas, also in computer science and in neuroscience and psychology and in management. And we manipulate zero intelligence through these parameter changes, and this can have policy implications. Yeah. So when you do policy implication, you cannot just say, oh, what's the rational expectation, and you then do that according to this target. Yeah, you have to think what other people think, and it's very different whether you are in an environment of strategic substitutes. So where basically you have this banging back and forth, or with complements. So in financial markets, which are typically markets with complements, you have to react differently than in markets where you have strategic substitutes. And this is what I wanted to say. Also the boundaries, I mean, the big news is also boundaries play a huge role. And boundaries are very important when you talk about bargaining. Yeah, so you have to think, what is the first offer, and you set the bounds with the first offer. Also in the panel system, yeah, in some countries you have no boundary, like in America you can have 127 years. Yeah, that makes a big difference. Or when you have, like in Germany, only 15 years of highest penalty. Okay, that's what I wanted to say. I don't know whether there's time for questions. I mean, we started a little later, so I don't know whether we'll find 5 minutes or not.
Oh, we have 10 minutes for questions.
There's still.
According to my watch, yes. I think we're perfectly in time. Thank you, Rosemarie. I think you have guessed very well what could be interesting for us computer scientists, namely the idea that we can play a game as if it would be a decision problem. So that somebody somehow can aggregate everything else in the system, and that we will construct the best reply, and that will work. And so you pointed out one that even if this aggregation is perfect, then you will invent an opponent that cannot exist, or may not exist in a particular setting. So when you said we have level 2, we have equilibrium, it would be best to play against the level 1 player, only that nobody plays level 1. I think this is an interesting point, that there is an operation that we do intuitively in computing, and that creates an opponent that wouldn't exist, but acting as if it would exist gives us the right results. Is my intuition correct?
About the existence, I mean, we can have models where actually nobody is a zero intelligence player. So this has been shown by others. I have shown here an example of your own data where you played 0 or level 1 or level equilibrium. Yeah, so 30. And the right choice was level 2, and nobody chose level 2. Yeah. So, I mean, this is the problem. I mean, with my experience, probably in these kinds of games, I would know more or less what what I should choose. Like when I play against undergrads, the 2/3 of the average game, I know I should choose somewhere between 20 and 25. Against more sophisticated, I should choose between 14. So knowing your target group is very important. And of course, this is what in marketing you do. I mean, when you launch a project, you always think of the target group. And if we don't know the target group and the preferences of the target group, you will ask them, what is your interest about a certain idea of a product? Yeah. So we are not in a black box entirely, because the level 1 is really, so if, for example, level 1 is very close to the equilibrium, then this is a good choice. Yeah. So if you need many iteration steps to the equilibrium, then you probably should not choose the equilibrium in the first period. Over time, there might be convergence. Yeah.
So I have to find out how to take questions. I understood there was a question from Stéphane Leroux.
I mean, you have to unmute everybody, or I have to allow them that they can unmute themselves.
Let me check.
They can unmute and ask. There is no problem.
Okay, yeah, they have this power. Okay, Stefan, can you? Yes, please.
Yes, it was actually a follow-up question. There was a question before, and I wanted to follow up to say that the size of the population may matter because when you choose 2/3 of the average, you're actually changing the average.
Yes. So your question is what?
It's more like a comment that there is a mathematical reason why the size of the population may matter.
Yes.
Even when one group plays against another group.
Yes.
Even
so I mean, of course, the median choice would be better. Unfortunately, the median is a little bit more difficult for most people. But if you have already more than 15, 20 subjects, then it doesn't matter so much. If you have a few subjects, of course.
But if a group plays against another group, as you did here, I mean, the workshop participants against the undergrads, then it's the ratio of the population that matters more than the size themselves. And even if the two populations are big, then the fact that when adding a number, you change the average.
So basically what we do is we replace one player, or we actually, what I didn't say, I didn't want to go into this detail. Everybody plays again. Yeah, this is the answer to your question. Everybody plays against the other numbers, the average of the others. Your own number is never in there. Yeah. So
okay,
you are playing against the average is always the average of 9 other players. Yeah.
Okay.
Yes. So then 100, and the average of the others is not changed. Yeah.
Okay.
Sorry, I didn't say that. I should have said it, given your question. But your question is very good, and we anticipated basically that of course, when you have to guess what others are playing, especially another group that has already played, it's better to play against the average of the others.
Thank you. Are there more questions? Maybe you just switch on your mic then. I'm not sure I see the raised hands. I see Jam has some questions.
Yeah.
Prakash, do you have? No, you have no camera. That's why you're different. Okay. Yes, Jam, please.
Okay. One question is what happens when you repeat? I mean, the same group repeats against the same group after having seen what has happened.
Yeah.
And then, like what you were talking about, like from experience, right? But I think that matters a lot for the firms, right? I mean, when you talk about competition, when you talk about competitors, I think history matters. So
yeah, I can show you a graph. Can you see this graph?
Yeah.
Yes.
Good. I'm prepared for this question. So indeed, in my thesis, I repeated 2/3 of the average and also 1/2, and another game also 1/2 of the median. And so indeed the numbers go down, and they go slower down if you have only 3 players. So here are 15 players. Here we play against the median, and for some reason in the fourth period, a lot of people, just for the fun of it, went up, but the median converges very nicely. Yeah, and then when you have 4/3 of the average, the numbers converge very quickly to 100. Yeah, this is the equilibrium. Yeah.
Okay, so you do have,
and I have actually, let me, I didn't show this because I thought I'm out of time, but I have an even better graph for that, and that's a paper by Meyer and Cass Holmes et al. So here I show you a game of strategic complement substitutes, so minus, so this is a yi, yeah, and the average is the expectation. So it's basically 0.9 minus 0.9 times the average, or 0.9 plus 0.9 times the average. And here you have bubble goods. So in the positive domain, you don't get convergence. In the negative domain, you get very nice convergence very quickly. And you have also plus C here. Yeah, so basically, this is 2/3 of the average plus 10 is here 0.9 times the average plus almost 120 or so, and here it's plus 3, and the equilibrium is always 60. So this is an even nicer experiment for that. Other questions?
another question. Oh, I see Stefan has raised his hand, but quickly, I'll ask this. This graph that you showed with the normal distribution under the general equilibrium model, would it hold for perfect computation?
What do you mean by perfect competition?
Perfect competition, I mean in a perfect market, like in Cournot or...
I mean, Cournot is not perfect competition. So an answer to perfect competition. So perfect competition is when you have buyers and sellers, and they form a demand function. We get always very nice convergence in double auctions. So that's, Vernon Smith got the Nobel Prize for that. Yeah, so you basically, every person has a cost. Yeah, you have signals there in terms of costs and
that's
for
like
the buyers and sellers, and willingness to pay for buyers, and they converge very nicely. Yeah, and it's not. I mean, it's this Shamsander and Goat actually produced their zero intelligence models in that kind of environment, and all you need, that's what I said at the beginning, you need basically a random behavior in the first period, and then the set shrinks according to the asks and bids. Yeah, so the selling and buying prices, and then you randomize within that, and then zero intelligence agents among themselves would also converge to the equilibrium. Zero intelligence agent would lose against buyer when they have buyers. If they are all sellers and you have buyers which are humans, they, zero intelligence would lose. I mean, they can be appropriated. But this is a good question, yeah, where basically you get nice convergence. Let me make another remark to this, if there's no other. Here, for example, I show you experiment where you have no knowledge of the parameters. So you don't know this 20 divided 21 and 123 or 20 in this tree. They know nothing. They just play. They play and they get paid according to the distance of the target value. And then they repeat, and you see it's the same subject. It has nothing to do with strategic sophistication. It's just the property of strategic substitutes and complements. And actually, in the targeting the inflation, the central banks, they introduce this kind of knowledge, and they make the markets more strategic substitutes by changing certain parameters, which, I mean, they can change the interest rate. Yeah, and by changing the interest rate, they can basically dampen the bubbles. Wow.
Mm.
Yeah.
So one little question from Stefan still.
Yes, in these sort of experiments, is there a standard time for the people to give the answer? Like, is it like 1 minute? Or?
Yeah. So experimenters have done everything. I mean, typically we don't give time limits. Yeah. But if you shorten the interval to give responses, then the behavior becomes less sophisticated. I mean, you see differences. Yeah. And you also see in these kinds of experiments, those who answer quicker typically answer more randomly than those who answer with more sophistication. I mean, in other games, you see a better separation between intuitive and more game theoretic answers than here in the beauty contest.
Thank you, Rosemarie, and to the audience. So we have a little break, 15 minutes, and if you like, we can meet on Gather Town, and then we can go around Rosemarie and talk to her.
Mm-hmm.
Yeah, so actually, so it's a geographical space. It means that well, there is.
And I will just stand somewhere and not move, because I'm afraid when I move, I disappear. I tried that.
We can follow you, but not everyone can do this.
Yeah.
So see you back.
I'm there now, and
Okay.
I see other people there. So if you
great.
see me.
Yes, I think, I don't know whether we need to switch out of Zoom for the moment, but we will do a little test for the next talk.
Yeah.
So thank you very much for
It's a
this
pleasure to
opening
talk to you.
session.
My first talk in India.
Oh yes, we should ask from the organizers a picture of how Goa looks right now. Thank you. So see you back in 15 minutes then. Thank you, Rosemarie. Jam.
I think Michelle wants to.
Yes, we will try the
slides.
Okay, I see there is one micro that has an echo. Is it mine? No, it was not mine. Somebody else, maybe. I switch off Rosemarie's. Yes, because Rosemarie, you are in Gather Town and here. Okay, I will switch. Okay, perfect. Jam,
I cannot share screen. For the moment, I don't have the option to share screen.
One
okay,
moment,
we make you host.
We'll make you host here.
Okay.
Okay.
Okay. So let me just catch my up.
Hello, Yoram.
Yeah, welcome, Yoram.
And I cannot see the raised hands. Maybe, I mean...
Yeah, you go to participants if you...
Yeah, I'm on participants, but I only see micros, cameras. I see no raised hands.
Not right now. Okay, I'll raise my hand and see if it happens.
Yeah. Yes. Now I see Bhaskar has raised a hand. Okay.
Yeah.
Maybe I just have to sharpen my eyes.
Does it work, please?
Yeah.
Yes,
and I
perfect. Wonderful.
Okay, just let me check one thing.
Okay, so we still see the yes, that's what I wanted to say, that we see the menu bar, but now it's gone. Now this is
you should see the full screen moving now. Is it okay?
Wonderful.
It's perfect.
Wonderful.
It's
perfect.
Okay.
Works very well.
Wow.
Okay, so I don't touch it.
You don't. You can have a break. Come together.
I'm too afraid to touch it.
Yes.
What about your video? Are you able to have it on as well?
I think for the video, I had problem both with the video and with the.
So with the microphone.
with the headphones. So where are you?
Ah, yes. Okay. Perfect.
I don't see myself.
Oh, we
Okay,
see
so
you.
maybe I will say hello and then I will stop it.
Yes.
And
perfect. Wonderful.
okay.
I go on Gather Town, see that everybody behaves.
Yeah.
See you there. I mean, yeah.
10 minutes. Yeah. See you.
10 minutes. Bye. But I will switch. I will mute everything.
So is our chair here?
I saw him and
Hello.
gather and told him.
Ah, okay. He cannot be far, Michel. Our chair.
Can you
No,
hear
he's
me?
here.
Yes, yes, perfect. We hear you. Bhaskar is here. Jam is here.
Maybe it's better now.
No, it was better before. I think you went too close now to the microphone.
And now, is it okay?
That is perfect.
This is
That
good.
is a very good
This is
distance. Okay, somebody has an echo, but it.
No, when the other mics get muted, the echo will go away.
Okay, good. No, you're coming too close. Yeah.
For the moment, I'm not speaking. You tell me when I start.
Amal,
shall we start?
Yeah, there is a.
Okay. Welcome to the second talk of the first day of the workshop. Our next speaker is Michel Delara. Michel Delara is a French applied mathematician trained in stochastic processes and in control theory. After graduating as an engineer at École Polytechnique and at École Nationale de Pont-et-Chaussée, where he is presently working. He started his career in the Environment Research Center while working part-time at the French Ministry of Environment. He is now in position at the Mathematics Research Center, CERMIX, where he belongs to the Optimization and Systems team and addresses different applications of mathematics and publishes papers in such diverse fields as biology, economics, and mathematics. Since July 2014, Michel Delara is a part-time at the Institute for the Energy Transition Efficacy as advisor on optimization of microgrids. His current research and teaching span stochastic control with a focus on the management of energies in the context of fast changes in the energy system. Over to you, Michel.
Thank you. I hope you can listen to me because the sound was poor when I heard you. I'm sorry. I hope it's okay when I speak. Is it okay?
Yeah, it is perfectly fine. Please go ahead.
Okay. So I'm going to talk about games in product form, and I want to thank my colleagues Jean-Philippe Chancelier, Benjamin Eman, Daniel Kadnikov, and thanks the organizer, especially Dietmar, for inviting me. So I'm going to consider an example. You take 3 people at a table, and each of them has 2 possible actions, 0 of 1. And there is the following structure. When the player to the left makes the action 1 and the player to the right makes the action 0, you receive the signal good. Else you receive the signal bad. And with this signal, okay, you can make a strategy that this signal will be the fuel of your strategy. So a mapping from good, bad to 0, 1. And you want to know, can I play? If every player selects a pure strategy, is there a triplet of 0, 1 that corresponds to that? The answer is yes. If you look, I hope you see my mouse, from play to signals to strategies to plays, there is an equilibrium in that. So there is a unique thing. But you cannot start the game. And you cannot write this game on a tree. So this kind of playable but non-causal structure will be one motivation for this talk. And especially my talk will be focused on strategic interactions with a focus on information. Information is one of the couplings between players in game theory. Not only payoffs and beliefs, but information. So who knows what and when. And for that structure, I mean, when we want to handle information, we have 2 main models in game theory. The tree model à la Kuhn, game in extensive form. This is an Alice and Bob example. So you have a tree. You have an extension by Allosferrer, Ritzberger, which are more complicated, different trees, but they are trees. And I'm going now to present the Witzenhausen model, which was not designed for game theory, but for control theory, that does not work on tree, but on product spaces. So my talk is mainly a tutorial on the Witzenhausen intrinsic model. I will hint, but really briefly hint at the links between product games and games on a tree. And the only result that I will stress in this talk is that we have, with my colleagues Jean-Philippe Chancelier, Benjamin Eman, an equivalent of the Kuhn theorem for games in product form. And all along the talk, I hope to convince you that the Witzenhausen model is a very good mathematical language for game theory to describe problems and interactions when you have no common clock. And for computer science, it might be interesting because of possibility for decomposition of problems. Okay, so I have many slides. I will not cover them all. Of course, I start with the Witzenhausen intrinsic model. I will call it the W model. So we have to speak of that: agents, nature, and information. So we don't have really agents in game theories. From time to time they appear. Agents are quite central in the Witzenhausen model. And I want to first make a caveat. If I, Michel, makes two successive decisions, I am two agents. So we have to distinguish an agent from an individual. Once we make that, I think some things become less paradoxical. So this is the model of Witzenhausen. You take A, which is let's say a finite, but it can be a countable set made of agents. An agent is a decision maker. He makes one action, only one, in this set UA. And that's one of the first novelty of Witzenhausen. You equip this decision or action field, you equip this set with a sigma field. So you have a measurable space. Second, you have nature. Nature is a little omega in a big omega set. Omega is equipped with a sigma field F. So you have another measurable space. So for the moment, everything okay. First idea, a product idea by Witzenhausen, you form both the product space that I call the configuration space. It's called H because Witzenhausen called it the hybrid space. So you have nature and all the actions of all the agents. And you introduce also the product sigma field. So you have a big configuration space and a big field. So let's have a look at it. If I have nature with two elements of omega plus omega minus, I have top right, top bottom and right left for one of the agents and for the other. I have a cube to describe all my possible configuration. Another novelty which is central in Witzenhausen model is the notion of information field. So an information field for an agent A is a subfield of the product field. We will see examples very soon. So for the moment, just accept that you describe the information of an agent by a subfield. So when everything is finite, a subfield can be identified with a partition. So this is an example of subfield. I'm not going to comment on it, just to illustrate what it is. For agent A, this is a subfield. Okay, so what is a W model? A W model is a sample space, nature, with a sigma field, a collection of agents' action sets with sigma fields, and the collection of agents' information subfields. The only axiom that we will take is an axiom of absence of self-information. I will comment on it. Absence of self-information means what? If I am agent A, I do not know, let's say, in advance, the decision I will make, because there is a paradox if I think that I am a single agent, if I make a confusion between agent and individual. But if I distinguish both, self-information is quite natural. Okay, so now we move to example to grasp the way we capture information in the W model. So I'll start with Alice and Bob. So Alice and Bob, Alice has top bottom, Bob has right left, sorry. My configuration space is the product. So you have all 4 possible outcomes in terms of actions. Okay, this is the configuration space. What are the fields? The fields are the trivial fields. Here they are. Nobody knows nothing. Alice doesn't know anything, so Alice is not able to distinguish the 4 points. They all look the same for Bob. This is the level 0 of the W model. Then let's go a bit further. We want to represent the fact that Alice knows Bob's action. So what do? Bob is the same. Bob cannot distinguish. But the partition of Alice is richer. Why? Because Alice, she can identify here on this vertical line that B played left. And here she can identify that B played right. So by this simple picture, we can capture the flow of time. B knows nothing, B acts, and Alice sees the action of B.
I have a question. So, of course, Alice knows what Alice would choose, no?
No, Alice does not know, she decides.
But in the picture before, can you go one before? Here, I mean, why do you say Alice doesn't know whether she chooses TA or BA?
Because I don't care. I don't care. I don't care about that. The information of Alice, in the information of Alice, there is no need to know what she will do. She just needs to know, I have to watch around me before I make a decision. But what I look around is not part of my information. It's not my decision. So that's why Alice does not know what she will do. Let's formulate it this way.
Oh, yeah. Okay.
Okay, if you add a coin tossing, it's a bit more complicated because you have nature. So your square has become a cube because you have this omega plus, omega minus. And then you can play with the structure. Okay, for instance, in this model, B knows nature because he distinguished omega plus from omega minus. And Alice not only knows nature, she also knows what Bob did. Okay, this one, I don't want to spend a lot of time of it because it was one of the paradox in game theory of somebody who drives a car and at the second turn does not remember if he turned at the first one or not. So the problem is that if you think in terms of players, you get paradoxes. If you think in terms of agent, you can solve it. So this is one picture when we can formulate the absent-minded driver in the W model by introducing special fields that are explained here below. But I'm not going to delve into that. I just wanted to give a brief panorama and examples of how you can represent information without speaking of tree. I just said there are agents and an agent observation field, information field, is made of nature and the action of the other agents. And this dependence is captured in an information field.
Can I ask another question?
Yes.
So in the one of the problems in the absent-minded driver paradox is, I mean, maybe you can go back to the 2 pages if that's okay with this information set, the previous one. That what is a move at such an information set? Because a move in an information set in conventional, I mean, Kuhn information set, the outgoing edges out of an information set have to be the same. So you make a move, and it has to be by definition the same no matter where you are in the information set. So one of the problems here is that if you make, say, move T, you can only make it at the first one. You cannot make it again at the second one because it's the same move. Yeah, you will never get to the second one. And there was a big confusion in the Rubinstein-Piccione paper on the, I found, in the absent-minded driver, that if you had a behavior strategy, that you could move twice randomly, independently. So my question is, does your model even allow moves that are associated with information sets?
Well,
is there even a connection to the fact that if you know something, you have to make the same action no matter where you are?
Okay, so first, it's not my model. I'm presenting Witzenhausen model, and what I'm trying to do is to incorporate it into game theory, which was not completely done by Witzenhausen. But I think for me, the tree model is full of confusion. And so in Witzenhausen model, we don't have this notion of move. We don't have this notion of tree. I just have an agent, and for each agent, a decision set. In this case, the decision set of the agent is ST, but it's indexed by the agent to make it clearer. So in a sense, they have the same action set at every move, but I don't want to mix the two models because for me, it's more a confusion. So we don't have this notion of move, but the agent, yes, they have the same structure for their decision set. There are 2 elements in it. I hope it answers your question, but maybe you will have more questions when the talk moves on, because I will speak of behavioral strategies later.
Thank you.
Okay. So in fact, now we have everything in place, but let's say it's static. I described agents, nature, information. Now the question is, can the actors play? And for that, we need strategies and a notion of playability that Witzenhausen called solvability. So strategies. Strategy in Witzenhausen model is a mapping from the configuration space to the action set of agent A, with the restriction that it is measurable with respect to information field of agent A. The good thing with this vision is that everything is formulated on the same set H. So this is the notion in game theory of a pure strategy. Being measurable means that when you make your decision, you do not know more than what is in the information field. For instance, if the information field of agent A is trivial, your strategy is a constant one. Okay, just a notation, the set of all strategies of agent A will be denoted by capital lambda A. So it's a product, and this product structure is really interesting. And compared to the tree one, I mean, both conceptually and for practical purpose. So let's give another example for strategy. What does it mean that you have absence of self-information? That means that the information of agent A looks like that. You can see UB, you can see nature, but you cannot see yourself. What does it mean? It means that your lambda A, which is a function of omega UA UB, in fact, does not depend on UA. This is another way to speak of functions that depend on some variable, but we speak with it in the language of fields. Let's have another look at, it's a Bob and Alice model inverted here, where Bob knows what Alice is doing. In that case, the player A is a sort of first player. Why? Because his strategy do not depend on UA and UB. They only depend on omega. But the second one can depend on UA and never on UB. So this is how we capture the dependency from fields to strategy. So one of the big innovations of Witzenhausen was this notion of solvability. So what's important is, for the moment, I never spoke of time. There is no clock, no tree, no progression. So you need something that tells you if every agent has a strategy, is there a form of compatibility? When nature makes omega, when everybody is equipped with a strategy, is there a solution to the system of closed loop equation that says that the action of agent A is the output of the strategy of A? So this is for the moment a problem that, as Witzenhausen noted, does not exist in Kuhn extensive form, because Kuhn extensive form is made on purpose so that you don't have closed loop equation, but you have sequential imbricated equations. And so Witzenhausen, who was quite aware of Kuhn and Omann's work, took another option. The option is that not to presuppose playability, but to make it a property which is desirable. So a W model displays the probability, the playability property when you take strategy for all the agents, you take nature, and you ask yourself, is there a common outcome? If the answer is yes, there is one and only one, you have playability. So for instance, if I take a sequential model where B knows nothing and A knows what B did, we always have a solution to the closed loop equation. Why? Because in fact, so I'm sorry, there is a confusion here between A and B, sorry. Because in fact, B plays first and he only observes nature, and A plays second because inside A can put B and C. Sorry for the picture. Okay, you have deadlock situation. This is a deadlock situation. EA can observe what B does. B can observe what A does. And they really can distinguish. Then you are stuck in deadlock. You can have 0, 1, multiple solution depending on the strategies. So
Michel,
really,
can I ask
yes.
a question? What would be the definition of perfect recall and something like this?
Please, can you be a bit patient? It's coming.
Sure. Okay.
Okay.
Yeah, sure. Thanks.
Okay, so once you have that, you can define the solution map. You take chance, omega, and since you have a unique solution to this system of equation, you give a name to it, you call it S lambda of omega. This is a generalization in control theory of the notion of state trajectory that is induced by feedbacks. You start from nature or from the first initial state, you apply the feedback, and you move in the state space and you make the whole trajectory. Okay, in fact, what happens is that when I gave the example of the sequential case, I hope this time it's written correctly. That means A is the first player, A is the first player, B is the second player. You see that the solution map can be made in an iterated fashion. You start with omega, you plug omega inside lambda A strategy, you get an action UA, and you plug this action UA and omega into the strategy of B. So you can go on iterating. Okay, what I've described now is what people, I think, call a game form. You take an omega, you take strategy, and you go into the configuration space. And this is, I think, what people call a game form with an outcome mapping. There are no payoffs, no beliefs. I don't need them for the moment. I'm just describing interaction strategies and output of pure strategies. If it's not playable, and we are trying to play with that in the theory, you get a set valued mapping. Okay, I hope I have time. I'm going to speak of causality because it's an ingredient for playability and a bridge with three models. And I will really skip the classification of information structure, which is one of the most interesting part, but I have no time. So this notion is quite useful, a cylindric extension. If you take a group of agents, a subset of agents, you define the subfield of the whole field, its nature, the own actions inside the group, and trivial outside the group. So this group is made, I mean, this field is made of nature and the actions inside the group. With that, you can define very interesting concepts. So we have a whole list of typology of models that were designed by Witzenhausen, except for the last one. So we have a proposition for perfect recall. The most interesting for us will be causal model, but I will skip that. So you have many things that you can define. Precedence relation. You can define a subsystem relation. This is all Witzenhausen work. You can define information memory relation, action memory relation. And with all these notions, you can provide a typology of systems. You can speak of static team, station, sequentiality. You can speak of partially nested systems, quasi-classical, classical, hierarchical. What we propose is parallel coordinated, so we can describe things. But I need to speak of causality. So what is causality? Let's take Alice and Bob. First, we have to understand what is a configuration ordering. What is an ordering? You have two agents. This is an ordering, A, B, or BA. So it's a mapping from 1, 2 to the agents. So if Bob knows nothing and Alice knows what Bob does, we have the feeling that the ordering A, B is not good. And we will say that it's not causal. Why is it not good? Because A cannot play first. Alice needs the input of Bob to play. This ordering BA looks good because if B is the first agent to play, B will play because he just needs nature. And then once he produces his action, Alice can take the action and makes a decision. So that's the way we need to speak of that. And we introduce some notation. You take the mappings from the natural numbers into the agent. And these are partially ordering of order K. If you map 1 to 3 into the agent and that your mapping is an injection. If you take sigma 3, you are just ordering partially 3 agents of A. Oh, just some notation. When I have a partial ordering, you can see it like that. The cardinality, of course, is K. The range is all the possible action in the image. The last element, kappa star, is the last element, and the first element are the first element. So we will have this breaking thing. Okay, there is a tree structure on the partial orderings, and this is causality. Sorry, this is configuration ordering. A configuration ordering is a mapping that takes a configuration and tells you along this configuration, A plays first, B plays second, C plays third, and so on till the end. So along configuration, you can say who plays in which order. And of course, you can define this thing. H phi kappa are those configurations that are ordered by kappa up to stage cardinality of kappa. So you can always ask yourself, I have a partial ordering, who is ordered along that one? The answer is those guys in the set H phi kappa. Okay, this is causality. As Witzenhausen said, it's only a problem of notation. Okay, so what is a causal model? And it looks like a tree. A causal model is that you have one configuration ordering, phi, that maps configuration into total orders with the property that if you take a partial ordering, so this is not sigma, sigma it's the whole one. This is a partial ordering, and you take an element in the information field of the last agent. So you want to know the last agent of my ordering, what does he knows? And the answer is what he knows is made of at most of nature, and what the guys before him, those in kappa minus, did. So this is being causal. Your information cannot depend on those who are coming after you. But with Witzenhausen, everything is captured with phi. Being before or after makes sense on these sets. So you take the trace of your field and you have that. It belongs to a cylinder.
So this is exactly as in normal game theory, no? Or what is different? What would be different here?
Normal game theory, I don't, for the moment, there's no notion of strategy in what I'm saying.
It's, well, information. If information could be actions of others, no?
I mean, informations are made of action of others, but I have to say the others before or after, and this is the way to speak of the others before and after, but without a common clock, without tree.
Okay, oh, the non-common clock is there. Yeah, that's it.
There is no tree here.
Yeah.
So in fact, what happens is that information is first. Possibly you have a time clock, but not necessarily. Okay, what happens is, what is the connection is that Witzenhausen introduced causality because when you have causality, you have playability in a sequential manner. And the fact is that the Kuhn model encapsulates causality in the tree, whereas the Witzenhausen model does not speak of tree, needs causality. So in a sense, that's what I did with Jean-Philippe Chancelier and Daniel Kalnikov, and Dietmar knows that. So we tried to make the connection. Causal W models, in a sense, can be embedded in trees, and trees can be embedded in causal Witzenhausen models. So the W model, in all generality, are larger. They cover more cases than the tree ones. And so this is the example at the beginning. This is the example of a system that is non-causal. It's non-causal because in a causal system, you need that one of the agents at least only observes nature, which is not the case here because there is no nature. So you should have a trivial field. There is no trivial field. So you cannot start, but you can play. I mean, the information structure are such that if everybody of the three agents, everyone chooses a strategy, there will be a unique outcome, but you cannot start this game. I'm gonna skip the rest. You have many examples in pre-simple agent model where it's very clear how you express dependencies between a principal and an agent. Okay, I'm going, I think I have 10 minutes, Dietmar.
Yes, you have 10 minutes. Actually, our time is still 4:30, but we might.
Sorry?
Yeah, you
Yes,
have 10
you have
minutes.
You have 10 minutes.
Okay, so I'm going to speak of what we did, our contribution with perfect recall and Kuhn's equivalent theorem. So for the first time, I'm going to speak of players. What is a player? A player is an element of a partition of the agents. So I'm partitioning the agents, and I can identify an atom of this partition with a player. So a player, you can see it as he's a team leader. He's leading his executive or her executive agents. Of course, you have pure strategies, and I can adopt the vocabulary of game theory. A pure strategy profile is made of an element, lambda p, for every player. And lambda p itself is a collection of lambda A belonging to AP. AP is the agent of player P. Okay, perfect recall. We are going to speak of perfect recall for one player. So just a notation, when I take a player and an ordering, I'm interested to know who in the range of the ordering is an agent of P. Okay, pure notation. And this is perfect recall. Okay, you take an ordering. You have a configuration ordering, which is fixed. It exists. It is supposed to exist. And then you take an ordering kappa. You take the last agent. And you ask yourself, what is in the information field of the last agent? And the answer is, in this information field, you have the actions and the information of all the agents that belong to P before kappa star. This is the notation to say that those agents are before because of the kappa minus. So this is how we propose to express perfect recall. Any agent in P, I mean an agent of player P, knows what those agents of P before him did and saw. Okay, now it's, I have to hurry, but if you are used to Witzenhausen model, we think that it's a quite natural definition. Okay, so then what can we do? We can try to mimic a Kuhn theorem. And for the moment, we have a result in the case of finite W models. So everything is finite, the agent, chance, and the action sets. In that case, you can easily define mixed strategy. There are probability distribution over the strategies of the player P. We introduce a notion of product mix strategy, which is that you desynchronize the agents inside P. It's just one probability distribution over the strategy of agent A. So you don't have to coordinate your agents. By contrast, in the previous one, you had a coordination of all the agents of the player by the mean of this joint probability. Now you don't have joint probability, but product probability. We also have the notion, the more classical notion of behavioral strategy. That means selecting an action at random. And okay, we have this theorem that says that if you take a playable finite W game and you have a player that is supposed to satisfy perfect recall, then for any mixed strategy of your player P under focus, there exists a product mix strategy. You desynchronize the agent inside the player such that they give the same probability on the outcome space. The outcome space here, because omega is fixed, is the product of all the actions of everybody. So here you have the mu P and you replace it with a pi P. Okay, and this is horrible, but in fact, this probability is the image, a push forward probability of all the mixed strategies of all the players on the product of all actions. And this push forward is made possible because of the solution map. The solution map takes omega, takes lambda, and sends you into the outcome space or the configuration space.
Can I ask a question?
Maybe, but I'm wondering if it's better if I have 5 minutes to finish and then the list of questions.
Okay.
Except if it's very limited to that, but I fear that the question will be more general.
That's okay. I can wait. No problem.
Okay, so we have one thing that's interesting. We do not need causality to express that. And in fact, if the game is not playable, we don't get a probability, but we get a subadditive measure. So we think there are some generalization. I will skip the rest, but we are working now on the case of the continuous case. So we are taking inspiration from Oman to do a Kuhn theorem with continuous Borel spaces. So it's technical, but we hope we can arrive at. So as I promised, I'm going to finish in 2-3 minutes, and then I'll take all the questions. I did not speak of preferences and beliefs. I spoke of game form, mixed strategy, but that, of course, we can endow every player with an objective function from configuration to the real numbers and with beliefs. We can do it if we want. But essentially for me, a game in product form would be a W model with a partition of the set of agents that I call players. Then with each player, I associate a preference relation on outcomes, and we can have many differences on what outcome is, and a belief on nature. And belief can be a probability, a capacity of whatever you want. So I think we have a very broad language to speak of games. I think we can incorporate most of the games used in game theory, except maybe for the continuous time span. I mean, differential games, but I'm speaking of a research agenda here. We can define the Nash equilibrium, no difficulty from the normal form. We'd like to speak of subgame, subsystem, connection between subgame. We'd like to define subgame perfect equilibrium. We'd like to speak of backward induction. And that's it. Can you, so I'm stopping here for the questions.
Yeah, thank you, Michel. Now let's take questions. Jam?
Yeah. Yeah, thank you. The kind of mixed strategy that you're talking about, is it that every agent has a source of randomization that is independent of all the other players? I mean, because you're taking products probabilities, right?
Okay, if I take a la Oman, I hope this slide answers your question. Do you see the slide?
Yes, I can. Yeah.
Okay. So this is a mixed strategy a la Oman. These ones are copy of 0, 1. And so MA, the agent A, has a large generator, and you go into his action set. So it can depend on every agent inside the player. When you have behavioral in the sense of Oman, so this is the way we retranslated this definition, agent A has its own single generator. And with that, you traduce independence. I hope it answers your question.
Okay. Yeah.
Other questions?
Can I ask a question, Amar?
Please go ahead.
Yeah. So I was wondering, you mentioned this circularity in the playability or the solvability condition. I was wondering, is there any way to deal with that circularity issue?
Is there any way to, to deal with that?
The circularity, and you have assumed in your results that that all these models that you have considered are playable?
Yes, I mean, okay, the example I gave at the beginning and in the middle was an example where you had circularity, but you could play. So it's a strange example. Of course, if you have a time arrow, if you know who plays first and then you can move on, you can resolve the circularity and do sequentiality. So Witzenhausen, I think he wanted this kind of general framework, and inside of it, speak of possible sequentiality, but the sequentiality in his model is not fixed in advance. It depends on chance and then on what people do. So this is the configuration ordering. So I don't know how to answer your question. Circularity is an issue, but if you have playability, it's no longer an issue. It remains a sort of computational issue. How do you start? But not a conceptual one.
Okay, okay. Thank you.
I think other questions can be taken in Gather. So let's thank Michelle again. Thank you. See you at Gather.
We have time.
We have time?
Yes, it's 4:30.
All right, then let's take further questions.
Yeah, 4:30, and the next talk is at 5, so there is time.
Yeah, please go ahead. Questions.
So the main part is, I mean, I know game theory, I think, well.
I cannot listen to you. Sorry, it was stopped. You started a sentence and then it stopped. Sorry.
Yeah. So to repeat, I mean, this is a so players basically, there's a timing issue. Yeah, so that's the main part, because like that players have different agents. That's not something really new, or
yes,
I don't know.
I agree. Yeah.
Like Freudenberg and Levine.
Maybe you should cut off your.
Understood the timing issue. I mean, that's what I see is, I think, very different to.
Yes, in fact, that's a difference. In a tree, you have a clock, in a sense, if I want to speak. Okay. In Witzenhausen, you don't have clock. You have information fields, and some of these structures are compatible with a clock. Let's say this is causality. Some are not. But those that are not compatible with a clock may be playable.
So I know one game in experimental economics where you enter the market and you have no clue on what, I mean, it's sequential entering, yeah? But you don't know when you enter, whether you are number 25 or 15 or 3. Is that something like what you model?
I mean, you could model that. Because with Witzenhausen, you just have to say, let's make a list of the agent and let's examine this agent, what he needs to know before making a decision. That's all. If it's static, he only knows nature, he needs to know nature, you have that. Then, of course, if you want to make it more interesting, you might need this configuration ordering, which is part of the model. So I don't know, in that space, I don't know this model, but I mean, if I say it a bit bluntly, you can model everything with Witzenhausen model. Then you have to put the focus. But at the beginning, you forget the tree. You just think in terms of agents and actions.
So can you make us, you know the centipede game?
I know very little.
I mean, the centipede game, it's 2 players and they play sequentially. Each one knows when to get in. Of course, if you don't know when what the other person has done before, you have just information sets that have not only 1 point, but several points. Yeah, I mean, if I don't know what the other person has chosen, then this would be an information set with several points. I don't know where he is. And this timing issue seems to be, I mean, otherwise you wouldn't say it's something different from what is, how it is modeled in game theory, where you don't have a clock. I mean, not having a clock basically means players play simultaneously.
Oh, no.
But the knowledge is as if they play simultaneously.
No. It doesn't mean that they play simultaneously, because it depends on the information structure. You don't have a clock, but the information may be such that in a sense it is compatible with a clock. What I call a clock here is a configuration order. So in the case of the centipede, I guess you have players. If they play, so you have two players. If they play sequentially, maybe it means that those players have inside of them a list ordered by the natural integers of agents. And maybe we can start the model this way. Agent T of player P, T is a natural number, an integer, and then you say something about the information field of IPT, the agent T of player P. And you say, okay, what do I need to, or what do I know? And you write that, and then you start to write the game.
I hope it is clear. Any other question?
I'm sorry, I got locked out.
So did you, I was saying that in the centipede, that I don't really know, I would start the modeling this way. You have two players, okay? You take a player P. I think, if I understood you well, the agent of player P can be indexed by the integers.
Yes.
Because there is this notion of 1, 2, 3, okay?
Yeah.
And so you take T is an integer, P is your player, and you ask yourself, what is the information field of of agent T in player P? And I think in your model, this information field would depend at most on nature and on the actions of the previous player. Previous makes sense because before T, you have T minus 1, T minus 2. And you can possibly include the actions of the other player. So I don't know the detail of the structure, but you have plenty of room for different information structures.
All right, let's take the final question, if there is any. Otherwise, we break together.
Bernard?
Yeah, please go ahead.
Sorry. So you said in the beginning the Kuhn model is full of, or has problems, I mean, of information sets. What if you have perfect recall? Do you still see any ambiguity in a game tree with perfect recall?
Sorry, it was very difficult to listen to you. I said,
one more time. I mean, you said the Kuhn model of a game tree with information sets has difficulties.
For me,
you said, yeah. I mean, and so I wonder which one, even if you have perfect recall, I mean, what would be something that you find deficient with the Kuhn model?
What for me personally, I found the word cumbersome in Oman's paper twice. He speaks of the cumbersome geometric model. What I find cumbersome is working on a tree. I don't have this intuition on a tree, and decomposing in a tree, for me, it's less natural than decomposing on a product space.
No, but I mean, yeah, but I mean, the whole point of the trees is that you can nicely draw it down, draw it, and then you follow. I mean, if you have anything sequential, and that's how we think, I mean, in many games, I mean, that's very nice to write down. I mean, there is the geometry there, and that's, I mean, products become hard to visualize in higher dimensions.
Yes, but if you one of our motivation was studying decentralized energy systems. In that place, you have actors. You don't know who plays first or second. You have no notion of time.
Yeah. Okay, so that's exactly, that was my question. I mean, so you have things where you don't have a sequentiality and where you want to have some sort of independence of describing.
Yes, I want to build my model without thinking of time first, but thinking of spatial interaction first. Let's say it this way.
Okay, thank you. That's, I mean, enough as a quick answer. Thank you.
All right, thank you, Michelle. Other questions can be taken in Gather. Thank you.
Okay, thank you.
Thank you, everybody.
Thanks.
Thank you.
Thank you, Michelle.
Yoram, you want to check your slides? I mean, share screen?
Sure.
Yes,
Why not? I should be made co-host, or do I just share screen?
It's on the way. So
yeah,
you
Dietmar is making you co-host. Yeah.
I remove. Okay. Okay, I can see your slides.
Okay,
Yeah,
great.
Yeah. Should we start a bit later because the break started really late?
Early.
Yeah. Oh no, but Yoram has to leave afterwards. No?
No, I'm flexible. So whenever I don't have to leave. I just wondered whether it was when you told me or, or when the website told me. So.
Oh no, it will not be 1 hour late. I just go to the Gather Town, see whether something's going on.
Yeah, we start in half an hour, 34 minutes.
No,
What?
half an hour. You mean that much?
We
half
have
an hour plus
35
4
minutes.
minutes.
Yeah. I mean, the official time is in 34 minutes, right?
Correct. Yeah.
All right. Is it 34? Okay. No. I thought we were already out of
there's
time.
plenty of time.
Okay. Wonderful. 34 minutes. Then.
Okay. So we'll see you then.
See you.
See you soon.
Dietmar, can you hear me? Hi, Dietmar.
Yes.
Where are you?
Oh, I'm in Zoom. Where are you?
This is Zoom. Okay. So
Yes.
yeah, I'm in both. But so Ram can't see me in the gather. You're not in gather, no?
I switched. Yes.
So Ram, are you in gather?
Rosemary, you were. I can't find you in gather. You are somewhere. I was talking to Michelle, but in some social space. But
Yeah,
I got your message, but I couldn't find you. So you're somewhere
yeah,
else.
I don't know how to move my cursor. So I saw Michelle, not really, but almost. I mean, like I could do a tracing somehow to him, but I couldn't walk to him because I didn't have the signs well.
Maybe if you have time after the session, we exercise this. We go there together.
Yeah. So, now I see somebody moving. I saw somebody moving. Michelle, I see Michelle moving by, but a little bit down the screen. So how do you move?
With the cursors.
So I have to, now I can move. Now here, whoops. Hi.
Okay, so that works.
I found you.
But we have a problem, we are too close.
You know nothing.
Yeah. Nothing is easy. It's a trivial field.
Yeah, but
Okay. We have an emergency a bit because there are mics from Gather that capture the speaker from Zoom.
Yeah, my phone is out.
Yes, let me check.
Dietmar, can you speak on Zoom to check that it works?
Okay, so one thing we have learned is that when we switch from between Zoom and Gather, we should switch off the microphone.
Yeah.
Michelle, can you hear us now?
Yes, I can hear you. I'm going to switch the microphone off. Because the talk is starting. When is the talk starting?
We start in 7 minutes. If
okay.
Madhavan.
Okay, so I have time for question, as people say, if you want. But on Zoom. So we agree that we are on Zoom now?
Yeah, we are on Zoom.
Okay.
Yes. Let's stay
I hope we are on Zoom.
Now, and afterwards, after the session, we go and Gather.
Now I know how to move. It's easy. Yeah. So I mean, this information thinking. I mean, the timing. I mean, the best is really to make a very concrete example and go from a game of game theory. I mean, with the normal information structure and everything, and then say, so now we go into the in the Kuhn tree. I mean, Kuhn information and see what we gain and what we lose. Yeah. So you have a reference point of game theory, and then I mean, you have, of course, you have done it basically in your talk, because you build all these different information sets. Yeah, you say basically, I don't care what I choose, A or B, and I either know that the other person has chosen T or B. Yeah.
I mean, so, I don't know if you have really a question there, but okay, I just want to express what an agent knows in terms of the action of other agents. That's my starting point. Dietmar, you wanted to say something?
Well, since I know less on the topic than Michel, it may be easier to explain because I'm between the two of you. So, Rosemary, one thing is that maybe you really don't know whether a decision was taken or not. Yeah, so you cannot model it. I mean,
You can model in game theory. Just have an information set. Like if we have a Battle of Texas, we just have an information set where I don't know whether you chose A or B. So that's
sure, it's true. But then you can have a huge choice of nature that chooses in which order somebody would move. Yeah, and I mean, you settle on the principle that there must be an order, and it is not known.
Yeah.
And I mean, here there is a way to explain that. I mean, you don't even know whether there is an order. You know? We don't start with the axiom that there must be an order. Maybe there is, maybe there is not.
But there are many things that can be done on a tree, so I don't doubt that.
Yeah. So I want to know exactly what cannot be done on a tree.
What cannot be done on a tree?
And we are done, no?
Is a game that does not start. I gave an example. And what is difficult to model on a tree are spatial structures that come before the timing. When you build a tree, you start by a chronology, and then you say, you put the information set. Okay, with the Witzenhausen model, you don't care about time, you care about interaction between agents, and then possibly there is a time arrow. So it's a different way to model things, but I'm sure that you can model many situations in both ways. I personally always found the tree structure very cumbersome because I don't have this intuition on tree, subtree, all that. That's all.
But for example, in a situation where you know that there will be two agents who agree, I mean, all you know is that they agree, and then there is the next step to think about. You don't know how they came to an agreement. Maybe the one suggested something, the other accepted, maybe the second one. I mean, you can modularize this. You can say there is one step in which they agree. And of course, there are not so many ways to agree on something in terms of information flow. So the example is not perfect, but you can completely abstract from this. You know? And then I think that computationally there is something very useful in this model, because you could talk about this huge space of different scheduling of agents without drawing a huge tree or without having something. You see, I mean, this distracts attention. Whether
there is a theoretical advantage too that was pointed by Witzenhausen, is that a tree with a continuum of action is not really done. Oman did it in a sequential fashion, but if you want that the action of a player lives in a continuous space, I mean, you have to take the tree a la Carlos Ferrer, Ritzberger. So you have to very complicated objects to manipulate.
So there are experiments with continuous time structure. I don't know whether you know anything of.
We will have to go to the next session, I'm afraid. And so, Madhavan, are you ready? You look
I'm ready.
Well prepared.
Yeah. I hope I can be heard.
Yes.
And there's not too much. There's a lot of background noise, but I'll switch myself off as soon as it starts.
Perfect.
Why don't we see the screen?
So that's what I don't know. I thought that you had done something.
Okay, let's check.
Because
Definitely,
it looked like
Yoram has to undo the curtain.
Yeah, it looks like some. Yeah,
That's
there it is. Okay.
Wow. Let's see, so
should I start or should I wait for another 1 minute?
Yeah,
Few
another
minutes.
minute. Another minute. Yeah.
Okay, so my clock says 17. Shall we go?
Yeah, we can start. Yes.
Okay. So welcome to the third talk of this workshop. It's a pleasure to invite Yoram Moses from Technion. Yoram Moses is very well known for his work on knowledge in the context of distributed systems. He has won both the Gödel Prize and the Dijkstra Prize. So over to you, Yoram.
Yoram, we don't hear you. You have to unmute.
Okay, can you hear me now?
Yes.
Very well.
Okay, sorry. So thanks very much for the kind introduction, and thanks for Dietmar and Ram for the invitation. I'm very glad to be here. I'm unfortunately would have been even happier to be with everyone in Goa now, but I guess I'm not special in that desire. In any case, this talk will be about something completely different or quite different. It's going to focus more on uncertainty and how do we obtain information from uncertainty. It's going to be, I basically want to tell you two stories, or talk about two fairly recent works that I was involved in. In one case, the source of uncertainty is timing. And the question is, how do we extract timing information in an uncertain world? I'll say more about that soon. And in the second case, it's more an issue of uncertainty that comes from failures, from the fact that some agents might crash and not be able to communicate with us. And that will involve a little more of strategies, or knowledge will come up a little more in the second part than in the first part. So these are two stories, but feel free. I'm not sure whether I'll get to go through my whole plan, but feel free to ask questions, interrupt. But in any case, this is more of a distributed computing talk than it is. I mean, it's not a game theoretic setting. In any case, the first part is based on a paper with my former student Asad Dan and colleague Rajit Manohar from Yale. And it started from some work that we did with Rajit on, of all things, modeling time in VLSI circuits, in the circuits that we build chips and computers from. I want to take a step back and talk about distributed systems. So if you have a set of computers, but you can think of them as agents. But a system is called asynchronous if we have no bound on well, agents have no clocks, and we have no bound, no guarantee about when agents get to move. So one might move 3 times when the other one doesn't move at all, and the second one might move 1,005 times. And and there's no guarantee, and a different execution of the same setting, of the same set of strategies, the ordering of their actions could be arbitrarily different. And moreover, there's also no guarantee about how long messages take in transit. So I send you a message, it's a little more like mail is today, as opposed to maybe a few years ago. I send you a letter these days, and there's no idea when it will actually reach you. So this asynchronous model is powerful because it assumes little, and any set of strategies that are guaranteed to work in the asynchronous setting will not be sensitive to things like timing and and so on. And so in fact, for example, the strategies, the protocols, the programs that run many things in the internet, the mail that we do, the web browsing we do, all that are actually based in large part on the asynchronous model. In any case, so we think of an asynchronous model where agents communicate by sending each other messages. And in those cases, we have very little information about time, but we do know some things. So for example, if Alice sends Charlie a message, then the sending event is guaranteed to happen before the message is received. The message was not received earlier than when it was sent. So even if we don't have any timing information, we're guaranteed that Charlie receives only after Alice sent. And this is true not only for a single message, but then if Charlie continues and after receiving Alice's message, sends a message to Bob, then we're also guaranteed that Bob received his message. Let's see if my pen was giving me problems. I guess it's, so this event here happens after the send event. Yeah, the pen doesn't work well. And in fact, Leslie Lamport, who was a very famous researcher in our field, defined in the late 70s, defined the happened before relation, where two events, we can say that one happens before the other if there is a message chain that starts after the first event and ends before the second one. And in fact, it turns out that if Alice performs an action, and then there's a message chain from her after that reaches Bob, and only after the message chain arrives, Bob performs his action B, then we're guaranteed that A happened before B. And that's quite obvious. I'm not saying anything deep. One interesting thing is that message chains, in a very precise sense, are the only way of ordering actions in asynchronous systems. So causality actually passes only through message chains when the system is asynchronous. Now, what I'm going to show in this first half of the talk is that if we don't have clocks, but we do have some timing information, then message chains are not the only way of ordering actions and of causally relating events. So I want to consider a situation in which it's not the asynchronous model, but we have bounds on how long messages take in transit. So suppose there's a lower bound on how long a message from Alice will take to reach Bob. Then we're guaranteed that an action that Bob will perform after receiving Alice's message will happen at least this lower bound between A and B time units. Okay, and we're going to focus on this relation that's here on the bottom left of the slide. A x b will be A, some event A happens at least X time units before B does. And this is enough to discuss. If we use positive and negative values of X, we can say that, well, A happens between 3 and 5 steps after B and things like that. So this, we're going to ask, how can we derive, how can we figure out when events stand in this happens at least X time units before relation. So our model is going to be, we have agents, they're connected by some communication network, and for every channel, for every edge between two neighboring agents, we're going to have a lower bound and an upper bound on how long messages take to go from the first to the second. Okay, so the picture here on the bottom right, if B sends C a message at time t, it will reach C no earlier than the lower bound, t plus the lower bound, and no later than t plus the upper bound. So in this model, I'm going to assume no failures. And what's important here is that we do have bounds on how long messages take, but I assume that agents don't have clocks, they don't have timers, and they don't have any other means of measuring time. The only way of measuring time is they know the bounds. The bounds are given to begin with, and the question is, what kind of timing information can they extract? So why no clocks and no timers? When is this sensible? Well, there are lots of systems. For example, we can think of biological systems, say the brain, as a big multi-agent system where the synapses, neurons, play the role of the service system. And many other biological settings. We have networks with information flow that we can model, and there is no clock in such a system. And similarly, often in the detailed circuits in VLSI, which is, as I said, where some of this work started, also timing has to be derived from within the system, and sometimes in asynchronous circuits, not with a clock, and there are other such settings as well. So any questions at this point? Anything? Is everything okay? I don't see the pictures for some reason, but okay, good. So let's go. So our goal, so our model, that we call this a bounded communication model. We have bounds on communication, no clocks, no timers. And the idea is, well,
I have a question. I mean, is
yes,
that now
Rosemary.
related to the previous talk? Are you in the same world as the previous talk where there also really no?
Not really. I mean, here I'm talking much more about time than about games. And at this point, I'm not, well, I'm going to talk a little bit about knowledge in about 20 minutes in this model, but I'm really talking about timing information in a model without clocks. So the thing that's connected is that there's no assumption of a common clock or maybe a guarantee, but here we do have bounds on how long things take. So the model is related, but it's not the same. We're not in the same, not in the same arena, really. But thanks for the question. And so suppose we want to ensure that we have two events. We're going to perform, say, A has been performed, and we want to perform B at least X time units later, or B will be performed, and we want to ensure that A will be performed at least X time units earlier. Well, how can we do that? Well, one, of course, you know, we already said if we have a lower bound on how long this message from A to B, from Alice to Bob takes, then we can perform an action at Bob, which is at least the lower bound after an action at Alice, by Alice performing the action, sending a message, and then Bob acting. Okay, so that's so in that case we can do it with X for the lower bound. We can do, and we can also use message chains for this. So we can, if we have a lower bound of X1 on messages from Alice to Charlie and X2 from Charlie to Bob, then if we perform an action at Alice, sent to Charlie, passes on to Bob, who then acts, then, well, we have at least X1 time units between the send from Alice received by Charlie and the X2 for the next message. And we can combine them and guarantee that B happens at least X plus and X1 plus X2 from Bob, from B. Okay, so one way of ensuring that two events are separated by at least X is by using a message chain and combining the lower bounds. And a question is this the only way? Is this essentially what we can do? Remember that in the asynchronous world, the answer was yes. I mean, in order to guarantee that B happens after A in the asynchronous world, this was the only way we could achieve it. So it's not a mute or trivial question, I mean, on the face of it. And the answer is no. And one way to see this is to consider a timing fork. So we have Charlie here sends, at the same time, sends a message to Bob and to Alice. Okay, and remember, we have upper and lower bounds on how long each one of these messages take. And the question is, what can we say about the arrival times of these messages? So we have a lower bound on how long a message from Charlie to Bob will take in transit. So it will reach there at T plus the lower bound, or later. And we have an upper bound on how long messages from Charlie to Alice take. And we know that this message will arrive to the left of this the red line on the bottom, on the timeline of Alice on the bottom. So in all of these things, by the way, time goes from left to right, and okay. So we know that in fact, the difference between the message to Alice will arrive before T plus the upper bound, and to Bob will arrive after T plus the lower bound. So if we take the lower bound from Charlie to Bob minus the upper bound from Charlie to Alice, call that X, we are guaranteed that the arrival at Alice is going to be at least X before the message to Bob arrives. Okay, does that make sense? I mean, this is an important point if there's a question, because, I mean, we don't have definitions, we have pictures, but that's the, okay, so if we take the lower bound to Bob minus the upper bound to Alice, this is X listed here, then we're guaranteed that an action, if Alice acts when she receives her action, her message, and Bob when he receives his, then we get that A's action is at least X units before B's action. Okay, does that make sense? So we can in fact coordinate the time between events at different sites without having a message chain between the two. Okay, and I should point out that, well, timing forks of this type are actually quite common in the design of circuits. And as I just mentioned, there's no message chain from A to B, and still we can coordinate the time between A and B. Okay. Now, one thing to notice here is that even though we don't have a message chain, there's a common point of reference. There's this Charlie who's coordinating these two actions. And one wonders whether this now is necessary. Again, remember, in the asynchronous world, we needed message chains. Here, we don't need message chain. We can use a timing fork. We can actually extend this idea of a timing fork to, say, a message chain going from going to Alice and another one to Bob from a common point of reference, and we would still have the same story. But the question is a common point of reference really necessary? Okay, and Asa, the first author on this work, was doing his master's, and was visiting Rajit, and we said, well, obviously that seems like the right thing, so please prove it. Or what are master's students for? This guy is extremely bright. And the next day he says, well, I failed. I couldn't prove it because I don't think it's true. And indeed, it's not true. And a way of seeing that it isn't true. So what is not true? It's not the case that in order to establish that A happens at least X time units before B, there has to be a common point of reference for the timing of A and the time of B. Okay, and how does the example go? Well, we have two timing. Suppose we have two timing forks, as we do in this example. And let's see if I do manage. And the point of arrival of the upper leg of this fork precedes the point of arrival of the lower leg of the higher fork. Okay, well, in this case, what do we know? We know that that here, the first arrival happened before the second one. So now, okay, I guess this is a nice animation. So the question is, I was going a little bit ahead of myself. So the question is, suppose we have these two forks. How close can we move A and B? Or how far back can we move B with respect to A? Well, obviously, we don't have, we only know, suppose we see these two forks, we don't have a clock. Well, the arrival could have happened at the lower bound from E to B, from Eve to Bob. And in fact, it could have been that the arrivals were very close to each other, because all we saw that one message arrived and then the other, and we can't measure how far apart. So maybe that's some very small epsilon. And now it's possible that in fact the message to David from Eve took the full upper bound. So we could, in that case, we can move the fork further back. And then, let's see, the animation here. Okay, so now it could be that the message from Charlie to David took the lower bound. So that is as the minimum it could. And it could be that the message from Charlie to Alice took as much as it could, which is the upper bound. So that's as close, that's as far back we can move B towards A, and as far forward we can move A towards B, but we cannot move them any closer to each other. So let's if that now is, if we call this difference x, then we have, if we have these two forks, we're guaranteed that A happened at least x before B. Okay, so let's remember with a fork, we had that the bottom of the fork happens at least lower bounds for the upper message minus upper bound for the lower message, as listed here. That was, and so we're guaranteed that if the arrival time, we call it A, and the arrival of the upper one called B, we guaranteed that A precedes B by at least x. And if we think of there being, so we call this a fork, and the weight of the fork in this case is defined to be x. Now, if we have two forks, then each one of them defines a time difference between the bottom leg and the upper leg. So x1 is the weight of the first fork, and x2 is the weight of the second fork. And now we know that the on David's timeline, on the middle timeline there, we have that the first fork ended before the second one began, or the upper leg of F1 arrived before the lower of F2, then we're guaranteed that, in fact, here A will precede B by at least x1 plus x2. Okay, does that make sense? I mean, these are pictures. Any questions? Any even? Is everyone with me? Nobody with me? Where do we stand?
There is a
Yeah,
hand
we are with you. Please go ahead. Yeah.
You are with me. Okay, good.
There is a hand raised. So Stefan.
Yes, Stefan.
Yes, just a short question. How does it relate to interval arithmetic with respect to addition?
Well, I mean, you can probably map this into interval, but I mean, the models are slightly different. So, but, I mean, obviously, I mean, as far as, time goes, the fact that time, is additive on linearly additive is not, I mean, that's not what's new here. What's new here is this idea that, in fact, you can relate events having with these, say, two forks. Okay, we call this a zigzag pattern.
Okay, thank you.
Yeah. And in fact, of course, you don't, I mean, two forks are just a special case. You can have any finite number of forks will give you a zigzag pattern like this. So what we learn is that you can actually derive information about timing, not just by messages and message chains, not just by a single fork, but also by a sequence of forks that are suitably positioned so that the upper leg of Fi ends before the lower leg of Fi plus 1. And one interesting, so we know that if there is such a zigzag pattern from A to B, then A precedes B by at least x. What's interesting is that it's guaranteed that A precedes B by at least x if and only if there is a zigzag pattern. So if there is no zigzag pattern of this type, then there is an execution which looks the same to all agents in which A does not precede B by x. So this is exactly the what governs timing in this bounded communication model. So So this is one way of guaranteeing, and it's the only way of ensuring or of concluding that A precedes B by at least X. But the story is not done yet. So first of all, let's take an analogy to message chains. If we have a message chain, actually messages are particular cases of forks, but this message chain allows us to derive that A precedes B by at least 0 time units. Okay. If we look at a zigzag pattern, is actually a chain of forks. So if before we had a chain of messages, in this case, in a zigzag pattern, you have a chain of forks. And the chain of forks allows you to derive our information. So a zigzag pattern can be thought of as a chain of forks with, of course, with a bounds. Now, well, another thing, so now the question is, fine, we've done this, but we want to strategize. So that, what do we mean by want to strategize? We want to use this in order to act in the appropriate way. And one thing, one very general result about sort of knowledge and action called knowledge of preconditions is that if something has to happen in order to perform an action, you have to know that it happened. So, you know, if the intersection has to be empty for the autonomous car to cross, then the autonomous car has to know that the intersection is empty. And in this case, in order to ensure that A precedes B by at least X, we've just seen theorem 1 saying there has to be an appropriate zigzag pattern that establishes this. Then that was the theorem. Then Bob has to know that this zigzag pattern exists in order to act. If Bob wants to act at least X time units after Alice has performed her action, then it's not enough for a zigzag pattern to exist. He has to know this. And the question is, when can you know such a thing? And let's go back to looking at message chains. In the case of a message chain, you can actually pass information from Alice to Bob. I mean, a message chain is going to guarantee some timing between A and B, but it can also carry information. These messages can actually have content saying, you know, Alice has acted, and this is the path. And so you can send a message. A message can actually be carried along this message chain. But in a zigzag pattern, that's not the case. You have a zigzag pattern, but even if Charlie sends this message to whatever it was, David or whoever, that message is not going to continue along the zigzag pattern, because there's no way of going back, you know, to the next fork and then to the next fork. Messages don't pass along forks. They pass along, you know, letters pass along in packages, not in forks. So in fact, in order to so the existence of a zigzag pattern does not mean that someone can know that the zigzag pattern happened, as opposed to the case of a message chain. And what we could show is that, well, we can characterize when you know there is a zigzag pattern. And I'll say just a couple of words. No way we can actually go into the details. But in order to know that a zigzag pattern exists between 2 points, one on the timeline of Alice and another on the timeline of Bob, one needs to know about each one of the forks and to know that the forks are ordered appropriately, where the upper leg of the lower fork completes before the lower leg of the next fork above. So we need these two things. And for example, for Bob, Bob can know about the zigzag pattern if there's a message chain starting a message chain, these purple or squiggly lines or message chains, informing Bob about the ordering between the forks. This the fact that Fi precedes Fi plus 1. So okay, that's what this was. And so a visible zigzag pattern for B is a zigzag pattern with message chains from the upper legs of the forks to Bob. And there's a similar, so now the thing is that the message chains are actually used for information passing. The forks are used for timing. So messages play two roles here. One is just to guarantee timing of events, like for measurement, because we don't have clocks and we don't have timers. They give us a way of distinguishing time. These are the red messages. And they also contain information about the fact that the fork exists, but the information about the ordering of the forks doesn't have to be, it can arrive in a message chain, which doesn't have to be direct or anything else. So we can similarly say, well, there's a slightly different for Alice. There's a definition of a visible zigzag pattern. And our main theorem there is that an observer, it could be Alice, it could be Bob, it could be anyone else, knows that there's a zigzag pattern with an appropriate weight x, which guarantees a distance, time difference of x between the lower leg of the bottom fork and the upper leg of the upper fork, if and only if there's a visible zigzag pattern connecting these two events. So, so in fact, what we learn is that, okay, we have three main theorems. One is it's guaranteed that A precedes B by X exactly if there's a zigzag pattern that shows this. In order to ensure that A precedes B by at least X, you have to know that there is such a zigzag pattern. And you know this only if and only if there's you have a visible zigzag pattern, a zigzag pattern that's visible to you with this property. So these are the three main results. Now, my slides sort of hinted at why the if directions of these, of theorem 1 and theorem 3 hold. And the main mathematics goes into proving that it's if and only if, that this is really a characterization of how we can obtain timing in this bounded communication model. So the conclusion for this is that bounds, just having bounds in a system with a lot of uncertainty about timing, it enables timing coordination. Timing forks and zigzag patterns are at the heart of the structure of timing in multi-agent systems. And that's the end of part 1. So it's a good point to pause for questions.
So Yoram, I have a question.
Yes.
So this message chains which inform about the message forks, right? So they will also be subject to these upper and lower bounds internally. So is it possible that you get different alternative bounds because of the message chains themselves?
You have lots of potentially lots of zigzag patterns, and the bound that you know is the best zigzag pattern you could see. Now these.
So is that, I mean, so okay, maybe that's a better question, the one you just asked. Then can you infer from this message chain the best zigzag pattern that you can see?
No.
Okay, not directly at least.
Not
okay.
that no, I mean, for the best one that you can see, you know, that's what you know about the timing, and then how do you figure that out? Well, that's okay. So that was story one, and it was a slightly.
A hand is raised, Yoram. Stefan has his hand up.
Yes.
Yes, maybe you said it and I missed it, but in order for a zigzag from A to B to be visible, it has not only to be visible by B or Bob, but by an arbitrary observer. Is that it?
Well, no, the definition is a zigzag is visible to agent I, to someone. Now, if it's Bob that needs to act after Alice, then he needs to know, so he has to have a visible zigzag. If it's Alice who wants to act and be sure that she's acting at least X before Bob, then the zigzag pattern has to be visible to her. But it could be anyone else, you know, for anyone to know about the difference between the time difference between A and B. The other observer. So for anyone to know that A precedes B by at least X, that agent has to have a visible zigzag to itself. Okay. Doesn't have to be to anyone else, but that talks about if you want to act based on this, then you need a visible zigzag to you.
Thank you.
Okay, great. So now for something again quite different, and this is based on a paper with another one of my students. I was very lucky to have a couple of, several, but
Yoram?
these are a couple of excellent students. Yes.
Can I ask a question?
Yes.
Yeah. So before moving on to the other part, then, the kind of, all the necessary conditions that you are talking about give some kind of epistemic constraints, right? Now, for coordination, it's not just knowledge, but you also want common knowledge. I mean, you are the one who got us into this. So I thought it was some kind of eventual common knowledge or something, but it doesn't seem quite like that.
No. So, well, there's a question. So in this paper, the assumption is, suppose Bob wants to coordinate his action with respect to Alice, and Alice is acting anyway. Alice, when she hears from Charlie, she's going to act, and now Bob wants to act at least so much later. Or, when Bob receives some message, he's going to act, and now Alice wants to act, at least 10 times steps before Bob does. So that was the game in that paper. Now there's another question, which is an open problem, which has to do with variation on common knowledge, which is how can we mutually decide, where you're going to choose an action or to choose when to act, and I'm going to choose when to act, and we want to guarantee that our actions are separated by X. And that in that case, I have to act knowing about a point where you will act, knowing about the point where I act, even though we don't have clocks. So we have preliminary work on that, but that's actually not a solved problem, and that's a variation on common knowledge.
Okay. Yeah. Thanks.
But thanks. It's a great question. So okay. So now I want to talk about silence, and uncertainty is going to come out of crashes. The paper is also called Silence, and it's with Guy Gorin. And we're going to start with a similar setting. Lamport, the same Leslie Lamport, pointed out in 85 that if there's a bound on how long messages take, so an upper bound, then there's a way in which we can send a message without sending a message. And the idea is that if I does not, so now instead of Alice and Bob, we have I and J from here on. And so if I does not receive a message from J until time t plus delta, delta is this upper bound on, say, the channel between them, if you like, then he says, well, then it's like receiving a message. It's I can discover that J did not send a message at time t. Okay, basically I timed out on you. You were supposed to send me a message at noon in case something happened. Well, it's far enough so that I know it didn't. That didn't happen. Okay, so a null message can actually provide knowledge. You're gonna send me a message by noon in case you're not coming to lunch. So at noon plus delta, I receive no message. I know that you're coming to lunch. So the idea here is that a null message can provide us with knowledge. So not hearing from you can give me knowledge, but that's true only if there's an alternative. That is, if there is, I can learn something only if it was possible for you to send me a message. If you never say, when you pass by my office in the morning, you never say good morning, and this morning you didn't say good morning, then I learned nothing. But if in some cases you do, in some cases you don't, I can learn something. So only if you would have told me something in some scenario, do I learn something from the fact that you did not send me a message. So that essentially says that we can't have a protocol in which, regardless of anything, whatever happens, everyone is silent, because that's not going to give us any useful information. So that means that, in fact, silence or choosing not to send can help us transfer costs among scenarios or save communication in some cases, but we can't just apply it always in life. I mean, I guess there are people who do spend long times in silence, but that's not in a distributed protocol usually. Yes.
But you have to be sure that the other process is alive, right? The process could have just died out.
You have a good point. You have a good point. So we have to assume reliability, and in particular, we have to assume that he's alive. So our model now, delta will be 1, and we have communication in rounds, and basically, if J is guaranteed to send I a message at time M in case some fact phi does not hold, then if I hears nothing from J at time M plus 1, remember now we're assuming that the delta is 1, then I knows phi at time M plus 1. Okay, so after you haven't heard from me at time M plus 1, I would have told you if phi was false. I told you nothing. You know that phi is true. Okay, so as Ram was telling us, well, if there's a failure, for example, if J could crash, he said he could die. Our notion of dying is crashing. Then if you don't hear from J at time M plus 1, well, do you know phi? Well, we already know. Jam just told us you don't know phi, right? Because maybe you didn't hear from J because J crashed. J's faulty, J died. And here you are on the right here, not knowing whether it's because he purposely did not send you a message or because he crashed. So you don't know phi. But you do know something a bit weaker. you know that either phi is true or J crashed. Okay, so in fact, in some protocols, in some protocols, it's enough to know this weaker fact that either phi is true or someone crashed, because, well, there are cases where if someone crashes, we're allowed to act differently. But the question that I want to focus on in the remaining, whatever, 10 minutes is, can we, I guess, yeah, well, we'll see. Can we silently transmit a fact phi even in a model in which processes can crash? So let's assume that there is a bound of f on the number of possible failures. This is common in distributed computing, where you design software that will be able to tolerate up to, say, 10 failures. If more than 10 failures happened, well, it doesn't have to happen. So it doesn't have to be correct. So this assumption is not that some of the animation here has a mind of it. It's also, now we're assuming that we have a model in which processes can crash, messages take one step, and the question is, can we pass information in this model? And the answer is, surprisingly, maybe surprisingly, yes. And that's because we have the bound on the time and also this bound of f. And how can I tell you, pass information to you without sending you an explicit message? I don't want to send you a message, and I want to inform you. And the way we do this is by constructing something which we call a silent choir. This group in the middle here, well, there should be f plus 1. No, my pen doesn't work. F plus 1. Okay, F plus 1 of these guys. And the point is that if some fact phi is false, come on. If some fact phi is false, then J, the conductor here on the left, will send a message to all of these guys. Okay? And if they all hear from him, then in the next round, they will be silent to I. If one of them does not hear from him, he tells the guy with the ear on the right here that no, I didn't hear from J. Okay, so if they all hear from J, they're all silent to I, and then I, after 2 rounds, knows phi. Okay, that's so we don't have to send this message to I at all. So we save this message. We spent f messages to begin with, but we don't want to count them, or no, we should count them. But in any case, this is a way in which we actually informed I of something without sending an explicit message. Well, in fact, we can use this to save messages if instead of sending to I, we want to, say, broadcast something to the world. And maybe if f is 5, you know, I tell 6 agents that all is well, and these 6 are going to be silent to the 1,000 participants in the Sun workshop, and they all hear at time 2. They all hear the silence, and they all learn that all is well. So we can actually save messages in some cases. But the interesting thing here is that here's a theorem saying, suppose Vj is J's value. J can start with either 0 or 1. And the theorem here says that I knows that J started with 1 at time m if either there's a message chain from J to I, or there's a silent choir of processes who know that the Vj equals 1 by time m minus 1. So the only way you can pass information by silence in this model is by constructing a silent choir. Okay, so this is one way of doing it, and it's the only way of doing it. It's like something kind of reminiscent of the fact that the zigzag pattern is the only way to guarantee timing here. A silent choir is the only way to pass information in this model, the crash failure model, without passing information. So, in fact, when we look at their works in the literature and solutions to various problems in which silent choirs are hidden, I mean, people did not know that they were constructing silent choirs, but it turns out that these things were used in slightly inefficient ways before, and they can be used in order to solve a problem efficiently. So I have 3 slides now which can fit the remainder of the time, but if we can, do we want to continue or do we want questions now? Because I guess I was kind of using my time.
So I think, why don't you just finish? Yeah, why don't you just finish?
Okay, yeah. Good. So I want to tell you about a popular problem in database systems, distributed systems, called atomic commitment. And the idea is you want to vote, and you need a unanimous vote. So more precisely, every process, we have n processes. Each one of them starts with a vote either in favor of committing or in favor of aborting, usually a transaction, but either in favor of saying yes or in favor of saying no. Now we want every process, has to eventually decide on one of these two. And all the processes that decide have to make the same decision. The model is still the model with F failures. So if you crash, you crash. Otherwise, everyone who doesn't crash has to decide, and they all have to make the same decision. But the point is that you can only decide to commit if everyone was in favor. Okay, if there was someone who was not in favor, you have to abort. And you're also allowed to abort if some process fails. So if everyone was in favor and nobody failed, then in fact, the decision has to be commit. It has to be one. Okay, so this is kind of a unanimous vote. Now, it's important in this case to have have solutions that are efficient in the case in which everyone is in favor and no one fails, because that's what happens in most cases. And it turns out, well, one can show that in such runs, you have to send at least n plus f minus 1 messages. And you can use that to show that, in fact, some information has to pass by silence. So you have to actually create silent choirs. A recent optimal solution for that was given by Gurauri and Wang in 2017. And the way it goes is essentially messages are sent along a ring, starting from P0 to P1, this ring here on the right. And so it goes from P0 to P1. So if everyone has 1, then P0 sends a message to P1 in the first round, and that continues to P2, P1 to P2, and so on. It goes all the way up to P0. And then for F more rounds, so n plus F rounds, there's one message in each case going around this ring. So, and then they stop. And then if all of these were successful, then they perform some consensus protocol. They go for another F rounds, and then they commit. And it turns out that essentially what happens here is that after the first N rounds, the blue arrows, they inform P0 that everyone had a 1. And then the next F rounds were a silent choir. And well, in our work, in Guy's work, we actually simplified this protocol somewhat. And what we did was, in the first round, everyone who has a 1 tells it to process P0. In the second round, if P0 heard from everyone, she sends everything is okay message to a silent choir, to F plus 1 or to another F processes. And then in the third round, they are all silent to everyone. And once whoever hears the silence in the third round commits. Now, if someone starts with a 0 or there are failures, then things take longer. But otherwise, we only have n minus 1 messages in the first round and F messages in the second one, and lots of silence to everyone in the third round. And we get a similarly message optimal algorithm, but it takes 3 rounds instead of close to 3n rounds or n plus 2f rounds of the previous protocol. And the reason is they had a less efficient way of constructing the silent choir and of using it. And we did that sort of directly. So in summary, here we saw that upper bounds enable silent coordination. And even though failures complicate silent coordination, when you have crash failures, you can use silent choirs to transfer information silently. And that, in fact, is the only way to transfer the information silently. And doing so, we can get direct and efficient solutions to problems. So even when processes can crash, time bounds enable us to coordinate. So, well, thanks. And I'm open to any questions. Sorry for going 1 or 2 minutes over, but.
Thanks, Yoram. Thanks, Yoram. Let anybody have any questions?
May I ask?
Yes.
So it reminds me of some old stuff. I'm getting old also. So this is all, I think it was called the failure discovery problem or something. And I remember in the PodC community, it was kind of beaten to death with all bounds, 8 failure models and all that.
This notion of failure detectors, is that what?
Yeah, failure detectors. So I was wondering whether this is also related, because what you are doing is, can it be built for failure detectors? I don't know.
Well, in this model, you kind of detect failures, by not, when you don't receive a message you should be receiving.
No. So what I mean is time bounds can be used for failure detection as well, right? In this sense. So
yeah. So
there can be
essentially. So one thing is that in a purely asynchronous system, there are some famous problems, some essential coordination problems that can't be solved. For example, consensus. And one question there, which this is not directly related, but just some background, is what is the least assumption on top of asynchrony that will allow you to solve consensus. Consensus is an agreement problem that's close to atomic commitment. It's a very fundamental problem. And so they characterize how much information you need or what do you need to assume about the abilities to identify, to detect failures? But they don't. Here, by synchrony, in this synchronous model, you have more power, because you can say, well, if Yoram is supposed to send Ram a message in round 1, and you don't hear from me, then you can just you can detect. So the synchrony allows more detection, but so I promised it would be very different from the two fascinating talks we had before, but I hope I cleared some of the uncertainty. Yes, Rosemary.
I mean, sorry, I make a relationship to what I know. So do you know Rubinstein's email message, where the two generals send messages, and at some point a message is not sent, or you don't know whether the general sent a message, and so you could not, I mean, basically they already know that they want to fight, but they still, I mean, this is this common
That's closer. That's much closer to common knowledge than to this. And there's also work in our community about how unreliable communication leads to failure of common knowledge. It's related, but technically it's not kind of. Neither of these is exactly that, but yeah. But we're.
I mean, you have basically one message that, I mean, you would think a message should have come, but it's not coming, and therefore it has a content. Yeah, somehow.
Yeah, the fact that the message did not arrive, that tells you that, you know, I tell you, well, if I'm not coming to lunch, I'll tell you by noon.
Yeah.
Now, a little after noon, you go to the restaurant because you know, well, of course, you know that I'm invincible, I never fail, like Ram suggested, and you know, I would have definitely, or you, alternatively, you know that assuming I haven't otherwise failed, then I'm coming to lunch, so you can maybe gamble on going there without too big a downside.
Yeah.
Oh. Yeah.
Yeah. Hi. Question.
Hi,
So, hi. So it's in the first part of the talk.
Yeah.
So do you also consider questions like finding these lower and upper bounds, given that you need some set of messages to be transferred?
No, but it's a very good question, and I think that it's a more, you know, currently valid question now that we have all this big data and you know, collect information, so we can have a model approximating the world based on what we've already sampled, and use that and maybe improve and go from actual knowledge to, you know, better and better you know, levels of belief. So where does our model come from is a very good question. These days, forming models is more you know, practically possible, and there are also lots of so I think it's a very, very nice question, but I haven't handled it, and it would fit very nicely, of course, with things I've said, but it's a great question, but I don't, you know, yeah, thanks for it.
Thank you.
So Dietmar, do you have?
Yeah. So Yoram, there's a question in the chat. So it says, is there any possibility of improving message complexity of the MST problem using this technique? I mean, are there any known results?
Well, some of the most famous, maybe the most famous MST protocol that I know of is in the asynchronous world, and so there you have to have message chains. If you're synchronous, maybe, but I don't know. I mean, I think one could consider using, I mean, both parts of my talk for different. I think these are like the first steps rather than the last steps in these directions. But so it's a nice question, but I have no insight. Except, I mean, the Gallagher-Humpley and Spira protocol is definitely in the asynchronous world, and there, if you don't have there, you don't have a bound, and all information passes directly rather than indirectly. So here I showed two ways of passing information without directly receiving a message chain from the source. In the asynchronous world, you get no information without a message chain from the source.
So
yeah,
we also wanted to. So I understood the forks and the zigzags. They help you to. They are good for lower bounds. You can calculate lower bounds from a zigzag. Can you also? But for silence, you need upper bounds.
No, I mean, if you can see a zigzag, you can use it. So even if you don't know what the best zigzag that you see is, but you see a zigzag, then that gives you knowledge about the difference between the timing of the two events. So if you see the best zigzag, then the best zigzag in your view, then you conclude, your best information. But you can use this for definitely for the upper bound. It's a question of how can you coordinate to move at least 5 steps after me. Well, if there's a zigzag that tells you that you're at least 5 after I would be, even though you don't hear from me, but you know that Charlie sent me a message saying go, and he sent a message to David, and Eve said, David tells you, well, he received Charlie before he heard from Eve, and so you say, now I'm 5 after you're moved, so I can move. So this is actually when can you act? So it's definitely an upper bound rather than a lower bound.
It's upper bound on the waiting time.
It's what do you need in order to be able to act? So it's the upper bound. I mean, you can use this effectively in order to choose when to act. So it's not maybe the words upper bound and lower bound are not the right terminology, but this gives you a prescription of what information do you need to identify in order to decide to perform an action if you want to act at least X time units after me. Or
actually, I was wondering whether you can derive deadlines from zigzags and so on, because you need deadlines for the silence. I mean, you need to know that. Well, now the deadline is gone. I mean, now it doesn't make sense.
So, I mean, these are two different works, and the zigzag is more. If you think, say, in probabilistic terms about the realization. So zigzag is you observe the realization of the times, and that tells you something concrete. And for timing out, you actually have to take the initial bound. So I haven't thought about using one and the other, but they're a little different in the sense that the bound you need in order to receive a null message from me, to learn something from the fact I haven't heard, it should be a bound, an a priori bound. It's just like a property of the model. That every message has to get to you by delta. And the zigzag gives you the realization. So it's or at least it's a bound in both cases. In any case, these are slightly different, but
thank you.
In both cases, we use the a priori upper bound, and one case the lower bound as well. But I mean, I'm wondering. I think that the zigzag story, I need to find the right physicist in order to actually, because I think